What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would grind to a halt, lights would go dark, and rocket engines would fall silent. And here's the thing, it's so rare that the entire world is competing for every single gram. Tungsten has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. That's a temperature at which most other metals would have long since turned to vapor. Annual global tungsten production ranges from 85 to 100,000 tons per year. But here's what's striking. Up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, showing just how valuable it is. Total global tungsten reserves are estimated at roughly 3 to 3.5 million tons, nowhere near the reserves of iron or aluminum. But here's what really matters. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that will flip your understanding of the metal-holding civilization together. Picture a massive underground mine somewhere in Vietnam, China, Russia, or Canada, the world's biggest tungsten producers. Deep in the Earth's belly, hundreds of feet down, lie ores containing tungsten. Not pure metal, but complex minerals, wolframite and scheelite. Wolframite is a compound of iron, manganese, and tungsten. Scheelite is calcium tungstate. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep underground. It's tough, dangerous work, requiring high-tech equipment and strict safety standards. Thousands of tons of ore get hauled to the surface daily by massive underground trucks. Powerful blasts shatter the rock, exposing the valuable ore. It's like a controlled earthquake in miniature. After the blast, the ore gets loaded into haul trucks with capacities up to 300 tons and transported to the processing plant. After extraction, the ore goes to a processing plant. Here it undergoes several stages to separate valuable wolframite or scheelite from other rocks. First, the ore is crushed in crushers and mills into a fine powder. Massive jaw crushers with deafening roars break down car-sized chunks into fist-sized pieces. Then the crushed ore enters ball mills, giant rotating drums filled with steel balls. In these mills, the ore is ground into an extremely fine powder, almost like flour. Next, various enrichment methods are applied, such as gravity separation, magnetic separation, and flotation. Gravity separation uses the difference in density. Tungsten minerals are heavier than waste rock. Magnetic separation separates weakly magnetic wolframite particles from non-magnetic impurities. Flotation is a process where the ground or powder is mixed with water and special chemical reagents in large tanks. These reagents selectively attach to tungsten mineral particles, making them water repellent. Air is then pumped through the mixture, creating millions of tiny bubbles. The tungsten mineral particles latch onto these bubbles and rise to the surface, forming a foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The resulting concentrate is then processed at metallurgical plants to obtain pure tungsten. This is a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent calcination to produce tungsten oxide. The concentrate is dissolved in alkaline solutions at high temperatures. Ammonium paratungstate, an intermediate compound, is then precipitated from the solution. This compound is calcined at temperatures around 1100 to 1500 degrees Fahrenheit, producing tungsten oxide, a yellow powder. Tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. Inside specialized furnaces, tungsten oxide is heated in a stream of hydrogen. The hydrogen strips away oxygen from the tungsten oxide, releasing pure metallic tungsten. The result is a fine gray tungsten powder, the foundation for every product that follows. It's from this powder that tungsten rods, bars, and other blanks are formed through sintering. The tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, forming a dense, durable material. Sintering temperatures can reach 5400 degrees Fahrenheit. At that temperature, the powder particles begin to fuse, creating a monolithic structure. The process takes place in furnaces with controlled atmospheres to prevent oxidation. One of the most critical applications is the production of hard alloys known as tungsten carbides. These alloys, combining tungsten with carbon, plus cobalt or nickel as a binding agent, rank among the hardest man-made materials. Tungsten carbide is created by heating tungsten powder with carbon at temperatures around 2500 to 2900 degrees Fahrenheit. Tungsten carbide crystals form, which are then ground into powder. This powder is mixed with cobalt or nickel, serving as a binder, pressed into molds, and sintered. Tungsten carbides are used to manufacture cutting tools, drill bits, milling cutters, lathe tools that can machine the hardest metals and alloys. Without tungsten carbides, modern mechanical engineering, metalworking, and oil and gas extraction would be impossible. 2 pounds of tungsten can become a drill bit capable of boring thousands of feet through rock, demonstrating its incredible efficiency. Tungsten is also widely used in the military industry for manufacturing armor-piercing shells and bullet cores. Thanks to its high density and hardness, tungsten alloys have excellent penetration characteristics, providing high effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is irreplaceable. It's used to produce filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components requiring high heat resistance and electrical conductivity. Because of its high melting point, it's used in the space industry for components subjected to extreme temperatures. High-temperature alloys containing tungsten are used in aircraft engines, turbines, and other devices operating under conditions of extreme heat. Alloying with tungsten increases the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with lower toxicity. Plus, tungsten is used to create ballasts and counterweights in race cars, aircraft, and yachts thanks to its high density. It's also a component in certain jewelry pieces because of its hardness and scratch resistance. Tungsten is one of the least abundant elements in Earth's crust, which makes its mining and production especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential but not yet explored resources, the total volume could be significantly higher. This is, of course, incomparably less than reserves of metals like iron or aluminum, which underscores its strategic value. Annual global tungsten production, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years it's been approximately 85 to 100,000 metric tons per year. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine being able to take a worn-out tool that's already served its purpose and turn it back into something new, without spending energy and resources mining ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is among the most advanced and efficient of all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, demonstrating its value and economic viability. Where does used tungsten come from? The main source of secondary tungsten material is, of course, spent cemented carbides. Those cutting tools, drill bits, and milling cutters made from tungsten carbide. After intensive use, they wear down, lose their edge, or break. Instead of tossing them in a landfill, they're collected and sent to recycling plants. Other sources include tungsten-containing scrap metal, leftovers from tungsten product manufacturing, plus certain electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of ore mining and initial processing. Recycling dramatically reduces tungsten production's environmental footprint. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production greener and more responsible. And so, after a journey from underground blast through grinding into powder, and through flotation with millions of bubbles, through chemical dissolution and reduction in a hydrogen atmosphere at 1800 degrees, through sintering at 3000 degrees, a metal is born with the highest melting point on Earth, capable of withstanding 6192 degrees Fahrenheit, a metal without which modern industry, aviation, aerospace, and medicine would be impossible. And the most remarkable part, nearly half of this metal is born anew from old tools, making tungsten one of the most environmentally friendly strategic materials of our civilization.
Imagine a material born from sand and stone, fired at temperatures exceeding 2000 degrees Fahrenheit, stretched into threads thinner than a human hair, then transformed into either building insulation, boat components, pipes, composite beams, turbine blades, or even heavy-duty industrial structures. This is fiberglass, one of the most underestimated materials in modern industry. At first glance, it seems ordinary. Insulation here, composites there, holes and panels everywhere. But beneath this ordinariness lies an incredibly powerful technology. Because fiberglass isn't just melted glass pulled into threads. It's a meticulously calibrated industrial process where chemical composition, melting temperature, drawing speed, protective coating properties, and subsequent processing methods determine whether the material becomes brittle garbage or the foundation for strong, lightweight engineered products. And today, we're breaking down how fiberglass is manufactured for industry, why it's simultaneously light and strong, what forms it takes, and how one of the most versatile materials in modern engineering is born from molten glass. Everything starts with raw materials, and here's one of fiberglass's biggest paradoxes. The base is incredibly simple: silica sand, limestone, soda ash, and a few mineral additives. But it's the combination of these ingredients that determines the fiber's future properties. Pure quartz alone needs extremely high melting temperatures, so manufacturers add substances to control the process and change the final product's characteristics. Additives can boost chemical resistance, improve electrical properties, increase strength, or tailor the material for composites and insulation. Industry uses different types of glass. Some work best for general applications, others for chemically aggressive environments, still others for higher mechanical strength. So, fiberglass production doesn't just start with dumping sand into a furnace. It starts with precise formulation. At this stage, the material still looks like ordinary mineral mix, but this is where its future role gets locked in. Whether it'll be cheap insulation, reinforcing fabric, or the foundation for complex composite structures. The next stage is melting. The prepared mixture gets sent into massive furnaces, where at temperatures around 2,500 to 2,550 degrees Fahrenheit, sometimes even higher, the raw materials transform into a uniform glass mass. Pure quartz requires even higher temps. But the key part of this stage isn't just the heating itself, it's controlling the state of the melt. The furnace is divided into zones so the material doesn't just melt, it purges bubbles, becomes uniform in composition, and hits the exact viscosity needed. If the melt is unstable, if impurities or air pockets remain, the future fibers will have weak spots. And in a material that needs to be both thin and strong, even microscopic defects are critical. Essentially, at this stage, the plant isn't just creating liquid glass. It's creating a high-precision industrial melt that has to behave perfectly in the next phase. Because what comes next isn't pouring it into a mold, it's turning it into threads. And for that, the glass needs nearly jeweler-grade precision in temperature and flow. The most impressive stage? Turning molten glass into filaments. Liquid glass flows to special spinnerets. The industry calls them bushings. These are plates made from an expensive, incredibly resilient alloy of platinum and rhodium. The glass passes through hundreds, sometimes thousands, of microscopic holes. From each hole emerges a hair-thin stream of white-hot material. But that stream isn't fiber yet. Real fiber is born in the drawing process. High-speed mechanisms literally yank the glass downward at tremendous velocity, and that force transforms the molten mass into ultra-fine continuous filaments. We're talking diameters measured in micrometers, several times thinner than a human hair. It's the drawing speed and rapid cooling that prevent the glass from crystallizing like ordinary, brittle material. Instead, you get an amorphous glass filament with engineered properties. And here's where you really see it. Fiberglass isn't just molten glass, it's a material born at the intersection of fire, velocity, and precision mechanics. But just pulling the fiber isn't enough. Glass by itself is brittle, and if you leave fresh filaments unprotected, they'll start getting damaged, rubbing against each other, and quickly losing their properties. So almost immediately after drawing, the fibers get a special chemical coating, sizing. This is one of the most underrated yet crucial elements of the entire technology. This coating doesn't just reduce friction and protect the fibers from breaking during winding, it also preps them for their future work in composites, improving the bond between smooth glass and the resin that'll later hold the fibers together in the finished product. The right sizing determines how well the fiberglass will interact with polyester, epoxy, or other matrices. In other words, this is where it's decided whether the glass strand becomes just a bundle of brittle fibers or a full-fledged reinforcing material capable of performing in real-world structures. Sometimes it seems like fiberglass strength is all about the glass itself, but in reality, much of it comes down to the chemistry of its surface. Next comes the transformation of fibers into semi-finished products. Threads are gathered into strands, rovings, wound onto spools, chopped into short fragments, formed into mats, fabrics, or specialized directional reinforcement structures. And this is where fiberglass splits into two major application worlds. The first is insulation. Here, the fibers are made more random, turned into a bulky mat, bound with special compounds, and you get a material that traps air incredibly well, which means it traps heat and sound. The second world is composites. Here, the glass fibers don't just sit in a loose layer. They become a reinforcing framework for resins. These combinations produce boat hulls, panels, pipes, profiles, tanks, industrial flooring, and countless other products. Some applications use woven roving, others use chop strand mat. Still others use directional knitted structures where fibers are oriented for specific loads. In other words, fiberglass isn't one product. It's a family of industrial forms that starts with the same thread, but ends with wildly different application technologies. The story of fiberglass and industrial profiles is especially fascinating. When glass fiber meets resin, it stops being just a bundle of threads. It transforms into a composite where each material handles its own job. Resin handles compression beautifully, locks in shape, and spreads the load. Glass fibers excel at tension. It's roughly the same logic as reinforced concrete, where concrete and steel rebar compensate for each other's weaknesses. This combination makes fiberglass light, strong, corrosion-resistant, and easy to mold into all kinds of shapes. One of the most important industrial methods is pultrusion. Fibers get pulled through resin and a heated die, producing continuous profiles with constant cross-sections. That's how you make beams, angles, tubes, sheets, grating, and other elements that work where metal is too heavy, rusts, or fails on electrical and thermal properties. That's where the power of fiberglass hides. It lets you create structural materials from what seems like an incredibly fragile starting point. So why is fiberglass both lightweight and strong? The secret's in the scale and structure. The thinner the glass fiber and the fewer defects on its surface, the higher its mechanical strength. And when lots of these fibers combine into a smart shape and work together with resin, you get a material with an incredibly high strength-to-weight ratio. That's exactly why fiberglass and fiberglass-based composites are so widely used in transportation, construction, energy, and manufacturing. It doesn't replace metal absolutely everywhere, but it works beautifully where you need a combination of low weight, corrosion resistance, electrical insulation, and solid mechanical durability. Plus, fiberglass can be adapted for different tasks by changing the glass composition, fiber type, reinforcement direction, and matrix properties. That's how you end up with a material that can be a soft insulation blanket, a rigid composite beam, or part of a complex industrial system. And all of it, from sand, minerals, heat, and incredibly precise technology.
The fastener industry is a true empire worth over $90 billion annually. And its flagship products? Massive bolts and nuts that hold our entire industrial infrastructure together. They're not just chunks of steel with machined threads, they're the result of a complete process involving metallurgy, high-pressure forging, heat treatment, and incredibly rigorous mechanical testing. One tiny deviation in material quality, shape, or tightening force can render an entire joint unsafe. In this video, we're going inside the production line that creates giant hex bolts and nuts to show how raw steel transforms into the mechanical foundation of the modern world. The production process for heavy-duty bolts and nuts begins with one fundamental stage: cutting raw blanks. Large diameter steel bars rolled from high-strength alloy steel are fed into industrial cutting machines and divided into segments with precisely controlled length and weight. Modern cutting systems use hydraulic shears or powerful industrial saws, producing clean square cuts that don't distort the metal's internal structure. Throughout the cutting operation, coolant is sprayed directly onto the contact zone to reduce temperature, minimize friction, and wash away metal chips. This maintains cutting tool stability and ensures the blank surfaces remain clean and free from thermal damage. Typically, bolt blanks are roughly twice as long as nut blanks, because bolts require additional material to forge the load-bearing shaft and head in a single production run. During one shift, each cutting machine can process thousands of bolt and nut blanks. Each cut takes just a few seconds, yet the allowable tolerance is extremely tight, because the final shape and mechanical strength of the product depend entirely on the initial dimensions of these blanks. After the blanks are cut, the bolts and nuts move to the heating stage, but the way heat is applied to each component isn't quite the same. For nuts, the entire steel blank feeds into a continuous furnace and is uniformly heated to a temperature range of 1900 to 2100 degrees Fahrenheit. Heating the entire body allows the blank to reach a fully plastic and uniform state. So during forging, the metal can flow evenly inside the die and form a solid hexagonal body before the internal hole is drilled and threads are cut. Temperature is tightly controlled to prevent surface burning while ensuring the core remains soft enough for proper forming. Bolts, however, are heated differently. Instead of heating the entire blank, only the head portion of the steel rod passes through an induction heating system. In a matter of seconds, the front end reaches forging temperature and glows bright orange-red, while the shaft behind it stays significantly cooler. This localized heating method concentrates energy exactly where the hex head needs to form, reduces overall energy consumption, and preserves the mechanical structure of the bolt shaft, which is the primary load-bearing section of the fastener. Right after reaching forging temperature, the blanks are transferred directly into the hot forging zone for shaping. For nuts, the entire evenly heated blank is placed inside a closed forging die, where a high-powered hydraulic press forces the metal to flow according to the die's shape, forming a solid hexagonal body. Under this intense compression, the metal densifies, and its crystalline grains reorganize into a tighter structure, making the steel denser and more uniform. Between each press cycle, the forging die is sprayed with a layer of high-temperature coolant and lubricant. This helps control heat, reduce friction, and protect the die surface during continuous operation. For bolts, the forging process focuses on the head section that was induction heated. The blank is positioned so the hot end sits precisely inside the die, and the press applies force, causing the metal to flow outward, forming the hexagonal head. At the same time, the die is also sprayed with the same type of high-temperature lubricant used in nut forging. When the fluid contacts the hot die, it instantly vaporizes and creates a temporary protective film. This prevents metal adhesion and ensures the bolt head forms cleanly, with sharp, clearly defined edges. Right after forging, both the bolts and nuts are dumped straight into large steel containers for natural cooling in the open air. For big components, this cooling stage typically runs anywhere from 30 to 60 minutes, and can take even longer if the steel mass is particularly heavy. This slow cooling method prevents thermal shock, minimizes the risk of microscopic cracking, and keeps both the shape and the internal structure of the metal stable before the parts move on to the next production stages. Once fully cooled, the bolts and nuts are transferred to the surface cleaning stage. At this point, they're typically loaded in bulk into rotating drum cleaners or vibratory tumbling machines. The rotating drum moves slowly and steadily, creating mechanical friction across the entire surface of the bolts and nuts. This process sharpens the hex edges and leaves the metal surface clean, dry, and uniform. In large-scale production lines, each batch can handle anywhere from a few hundred to several thousand parts at once. Tumbling time usually ranges from a few minutes to several dozen minutes, depending on the size of the parts and the level of oxide scale stuck to their surfaces. Once the surface is cleaned, the bolts and nuts move to the identification marking stage. For nuts, markings are stamped directly onto the hexagonal body, while for bolts, markings are placed on the top face of the head. These symbols indicate the strength grade, technical standards, and manufacture of each part. They function as an official ID card, mandatory for bolts and nuts to be approved for use in industrial structures, heavy machinery, and large-scale construction projects. Once they've achieved their final shape and received their identification markings, bolts and nuts enter one of the most critical stages of the entire process: thread machining. The threading process for bolts typically begins with a light finishing turn on the shank to achieve a precise diameter and a sufficiently smooth surface. On the lathe, the bolt is firmly clamped and rotated at a steady speed, while the cutting tool simply glides over the surface to correct dimensions before threading. After this, the workpiece is transferred to a thread rolling machine, where 2 or 3 thread rolling dies, engraved with the precise thread profile, press against the shank under high pressure. Thread rolling is a cold-forming process that doesn't remove material but rather deforms the surface of the shank, creating threads through plastic flow of the metal. This produces stronger threads with improved fatigue resistance compared to threads cut by a cutting tool. For nuts, threads are created through the tapping method. First, a specialized drill bores a vertical hole through the center of the hexagonal body. Then a tap, a rotating cutting tool with external threads, is inserted into the hole. As it advances, the cutting edges of the tap shave material from the hole wall, forming a precise internal thread profile. During the tapping operation, cutting fluid is continuously supplied to cool the cutting edges, lubricate contact surfaces, and flush away metal chips. Once threading is complete, both bolts and nuts move on to final quality control. First up are geometric checks: diameter, thread pitch, thread depth, concentricity, and sharpness of the thread profile. Threads must match standard thread gauges perfectly. Even the tiniest deviation means rejection. Next come mechanical tests including surface hardness, tensile strength, and torque resistance. Only after passing all these tests do bolts and nuts move to packaging. At this stage, the products are no longer semi-finished parts. They're full-fledged structural components, ready to ship to construction sites, power plants, steel bridges, or drilling rigs, where every bolt and nut will be responsible for holding together massive industrial systems. From raw steel rods through cutting blanks, heating, forging, thread cutting, inspection, and packaging, giant bolts and nuts complete a manufacturing journey that's precise down to the tiniest details. If you find this journey fascinating, hit that like button to support the video, drop a comment to share your thoughts, and subscribe to the channel to keep exploring the production lines that quietly keep our modern world running.
Every year, over 27 billion square feet of drywall are produced in the United States. That's enough to build a road from the Earth to the Moon and almost halfway back, or to cover the entire state of Delaware twice. But how does an ordinary stone, formed millions of years ago at the bottom of ancient seas, turn into the smooth sheets that become the walls of our homes today? In this video, we'll take a look behind the factory doors, where tons of stone pass through furnaces, mills, and conveyors to become the symbol of modern American construction. Watch until the end, and you'll see secrets that are rarely shown publicly.
The numbers behind drywall production in the United States are not just big, they are astronomical. And they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of gypsum board panels. This number is so colossal that it's hard to comprehend. Try to imagine, if you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire state of Delaware twice and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator.
The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and in construction. It all begins not in the workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that was formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of the primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then, this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something resembling coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and essentially, it's the controlled drying of gypsum. The fact is that in the crystal structure of natural gypsum, water molecules are locked in.
For drywall to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum tilted at a slight angle. Inside this kiln, a very precise temperature of about 300 degrees Fahrenheit is maintained. The gypsum powder, slowly tumbling inside the drum, heats up and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but to put it simply, it becomes thirsty. Now this powder, which is already called building plaster or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that is the basis of the entire production. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line.
And now the most spectacular part begins, the creation of the sheet itself. In the workshop is a huge conveyor, hundreds of feet long. At its beginning stand 2 giant rolls of special dense paper, or paperboard. One roll for the face side, it's perfectly smooth, white. The other for the back side. It can be a bit darker, grayish. The ribbon from the bottom roll, the face side, is unwound and lays on the conveyor, forming an endless track. In parallel with this, in a giant mixer, resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it.
Each additive plays its role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to stick better to the paper liner, and fiberglass adds strength. This mixture, called slurry, resembles a thick gray porridge. It is poured in a continuous stream directly onto the paper ribbon moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded up, forming the sides of the future sheet. And at this moment, the second ribbon of paper from the back roll is laid on top like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers or under a forming plate, which compress it to a precisely specified thickness, for example, ½ an inch. The newly formed, still soft and damp sheet of drywall continues its journey on a very long conveyor called the setting line. Its length can reach several hundred feet. While the sheet slowly moves, a real miracle is happening inside it. The gypsum powder reacts with water, the same rehydration reaction occurs. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt, and at the right moment, makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very damp. They contain excess water that did not participate in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most massive structure in the factory, a multi-deck drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is very carefully controlled. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer appears a product we are familiar with, a perfectly dry, light, and strong sheet of drywall. But this is not the end. The final stage is finishing. 2 finished sheets are stacked face to face, their edges are perfectly trimmed to be straight and clean. A paper tape with information about the manufacturer and product type is glued to the end. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even stacks on pallets. Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will go to construction sites to become part of someone's home, transforming from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is booming, people actively build new houses and renovate old ones, and the demand for drywall soars. The factories that produce this product operate at full capacity, and the stream of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall factories are located throughout the country to be closer to large construction markets, the extraction of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa.
Every year, hundreds of oil platforms get installed in the world's oceans. Each one weighs tens of thousands of tons, and at some point, all that weight hangs from a single hook. Not a cable, not a beam, but a hook. A piece of forged steel that looks like a giant fishing hook from another dimension. Around it, the North Sea, a storm, 30-foot waves, a crane swaying on the deck of a ship. And the hook holds. It holds 8,000 tons. That's roughly the weight of 8,000 cars lifted simultaneously above the water's surface. One invisible microcrack half a millimeter wide, and a structure worth billions of euros plunges to the bottom along with everything attached to it. How do you forge a monster capable of holding 10,000 tons in the middle of a raging ocean from molten steel at temperatures exceeding 4,000 degrees Fahrenheit? And what critical moment do manufacturers carefully hide from prying eyes? Watch until the end. The answer will surprise you. It all starts with choosing the metal. For giant crane hooks, they use special structural steel where the carbon content doesn't exceed 1%, while chromium additives up to 2% and molybdenum up to 0.5% deliver tensile strength exceeding 145,000 pounds per square inch. These elements aren't chosen randomly. Chromium provides corrosion resistance for marine conditions, and molybdenum prevents brittleness at low temperatures because a hook might operate in the North Sea, where in winter the water barely stays above freezing and the air gets even colder. The raw material arrives as briquettes or ingots weighing 44,000 pounds each. They're loaded into powerful electric arc furnaces with a 440,000 pound capacity. Giant vessels 30 feet tall with graphite electrodes 24 inches in diameter. Steel for these hooks comes primarily from Scandinavia, where it's melted in vacuum furnaces with special composition control at every stage. The logistics are impressive even before production begins. 44,000-pound ingots arrive by barge right to the factory docks. If you're curious how things are made that human lives depend on in the open ocean, subscribe to the channel right now and hit that bell so you don't miss the next episode. When a current of up to 100,000 amps flows between the electrodes and the metal, it creates an arc about 20 inches long that heats the furnace contents to over 3,600 degrees Fahrenheit. This isn't just hot, this is the temperature where steel stops being a solid and transforms into glowing liquid. The furnace slowly rotates for even mixing, while gases are drawn off through powerful filters. The melting process takes 4 to 5 hours, during which the metal is purified through vacuum evaporation and argon purging. The finished melt, a bright yellow color, is poured into ladles lined with fire brick. The temperature at discharge, around 3,000 degrees Fahrenheit. Cranes lift the ladle and transport it to the casting line, where prepared molds are already standing. Massive steel structures weighing up to 200 tons each. The mold geometry is calculated accounting for 2% metal shrinkage. If you don't build in this allowance, the finished blank will come out smaller than required. They pour at a 45-degree angle to avoid air pockets. A stream of liquid metal about 20 inches wide fills the mold in 10 to 15 minutes. Then they seal it with a lid and move it into a controlled cooling zone. And this is where one of the most critical stages of the entire process begins. For the first 24 hours, the temperature drops only to around 1,500 degrees Fahrenheit. The next 2 days, down to 400 degrees. Full cooling to room temperature takes up to a week. Sensors continuously monitor temperature gradients at a depth of 4 inches. The slightest variation can cause thermal stresses that lead to internal cracks, invisible from the outside. During cooling, the metal crystallizes, forming a coarse structure that's later optimized through heat treatment. Workers in protective suits monitor the process through viewing panels, while automated systems record thousands of parameters every minute. The finished blank weighs between 100 and 200 tons, stretches up to 40 feet long, and measures up to 6.5 feet in diameter at the base. Once the lengthy cooling period is complete, the workpiece is pulled from the mold, using cranes rated for 300 tons and transported to the forging shop, a massive facility covering 22,000 square feet with ceilings 80 feet high. Here stand hydraulic presses capable of exerting up to 50,000 tons of force. That's not a typo. 50,000 tons of pressure on a single point. For comparison, the Eiffel Tower weighs about 7,000 tons. These presses push 7 times harder. The workpiece is cut into sections 20 to 26 feet long and reheated in gas furnaces to 2,200 degrees Fahrenheit. The metal glows bright red and becomes malleable. Workers in heat suits use magnetic grips to position a section under the press. First stage, rough deformation. The press descends with up to 10,000 tons of force, compressing the metal by 20 to 30% in a single cycle. Each strike lasts seconds, gradually transforming the cylindrical blank into the recognizable silhouette of a hook. Next comes intermediate forging. The metal gets stretched out, they shape cable holes up to 2 feet across and lugs 6 inches thick. The presses are equipped with complex dies made from high-strength steel, matching the exact geometry of the future hook. Total forging cycles: up to 50 per section, with breaks for reheating every 10 to 50 minutes. Between press strikes, they constantly flip and reposition the workpiece. This ensures even densification of the metal throughout the entire volume. Forging doesn't just shape it. It improves the internal structure of the metal, refining the crystalline grain and multiplying the strength compared to the cast state. The final forging stage: precision work on the working section. The main arc of the hook reaches over 3 feet in diameter, wall thickness 12 inches, bend radius 8 feet. The press dies work with accuracy down to a fraction of an inch, forming reinforcement ribs and flanges. After each strike, they blow off the scale with compressed air at 90 pounds per square inch. After forging comes heat treatment, a stage without which the hook would be just a pretty but unreliable hunk of metal. The piece is placed in a furnace for tempering at 1200 degrees Fahrenheit for 20 hours. This relieves the internal stresses built up during forging and gives the metal the necessary impact toughness. Then comes machining on milling equipment. Surfaces are ground to specified roughness. Mounting holes are drilled. Threads are cut into the attachment points. Each hook weighs between 50 and 150 tons depending on load capacity. Manufacturing takes anywhere from 3 to 6 months. The plant produces up to 20 of these units per year, and each one costs millions of euros. They go to crane companies that install oil platforms in the North Sea, the Persian Gulf, and off the coast of West Africa. Now here's where it gets really interesting: ultrasonic testing. This is where manufacturers hide a detail they'd rather not talk about. Every hook gets checked for hidden cracks. Sensors scan the metal with a 5 MHz wave, detecting defects as small as half a millimeter. If even one microcrack shows up, the part gets scrapped. No negotiations, no exceptions. Why is this so critical? Because these hooks work in conditions where failure isn't an option. An offshore crane lifts a platform section weighing 8 to 10,000 tons to a height of 100 to 130 feet above sea level. Waves slam the vessel's hull, the crane sways, the load cycles constantly, slackening slightly, then building again. These cyclic loads are especially dangerous. They make cracks grow even when the overall stress stays within design limits. Under these conditions, a microcrack that slipped past inspection turns into catastrophic failure within weeks. That's why every hook gets tested not once but multiple times. Ultrasound, X-ray, magnetic particle inspection, load tests up to 120% of rated capacity. After passing all inspections, the hook's surface is coated with an epoxy layer 200 microns thick to protect against saltwater corrosion. Then they apply the markings: serial number, steel grade, manufacturing date, and load capacity. This is the hook's passport, which will follow it throughout its entire service life. The global fleet of offshore cranes exceeds 4,000 units, of which around 1,200 are floating vessels with lifting capacities above 5,000 tons. Hook production for them is concentrated in Europe, primarily in the Netherlands, Norway, and Germany. And total output across the entire industry comes to just a handful of units per year. The finished hook is loaded onto a specialized platform and shipped to the vessel. There, in the open ocean, they'll attach a cable to it, hook a platform section to that cable, and this piece of forged steel, born from molten scrap, will single-handedly hold the weight of several hundred railroad cars. Waves, wind, rolling seas, and it holds. Because every press strike, every hour in the furnace, and every pass of the ultrasonic probe were done with zero margin for error. What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged: heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy: the process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening, because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry, and remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2,000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers, entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
The Caterpillar 3618 engine, 18 cylinders, 88 gallons of displacement, 7,200 kilowatts of power, 9,655 horsepower. One engine weighs 79,000 pounds. The piston in this engine, 11 inches in diameter, 11.8 inches of stroke, 50 pounds in weight. This is Caterpillar's largest piston. How do they make it from liquid aluminum? Today you'll see the complete production cycle of a giant piston, from an aluminum ingot to a part that moves at 33 feet per second and withstands 2,685 psi. If you want to see how they make the heart of a giant engine, subscribe to the channel. Here we show you the factories that move the world. The Caterpillar 3618 engine is designed for high-speed marine vessels, ferries, patrol boats, yachts. A single engine produces 9,655 horsepower at 1,050 revolutions per minute. It's a V18 four-stroke diesel. Cylinder bore is 11 inches. Stroke is 11.8 inches. Displacement per cylinder is 1,130 cubic inches. 18 cylinders total, 20,330 cubic inches. Compression ratio 12.6 to 1. Maximum cylinder pressure 2,680 psi. That's 185 atmospheres. Combustion chamber temperature 3,600 degrees Fahrenheit. Mean piston speed 34.4 feet per second. The piston travels 11.8 inches in 0.028 seconds. Up and down 1,050 times per minute. 70 million cycles over 10,000 hours of operation. The piston material has to withstand all of that. The piston is made from an aluminum alloy. Aluminum is lightweight, density of 169 pounds per cubic foot. That's 3 times lighter than steel. Aluminum conducts heat well. Thermal conductivity of 133 BTU per hour per foot per degree Fahrenheit. That's 5 times better than steel. They use alloy 2618. Composition: 92% aluminum, 4% copper, 1.5% magnesium, 1% nickel, 1% silicon. Copper provides strength at high temperatures. Magnesium increases hardness. Nickel reduces thermal expansion. Silicon improves casting properties. The alloy arrives in ingots. Shape: a cylinder 12 inches in diameter, 3 feet 3 inches long. Ingot weight: 353 pounds. Before forging, the ingot is cut into blanks. Blank length: 12 inches. Weight: 84 pounds. This is the blank for one piston with extra material for machining. The blank gets loaded into an induction furnace. Temperature: 895 degrees Fahrenheit. Heat time: 30 minutes. The aluminum softens. Doesn't melt. Melting happens at 1220 degrees. We need plasticity for forging. The heated blank transfers to a forging press. Hydraulic press. Force: 10,000 tons. That's 100 meganewtons. The blank sits in the lower die. Die made from heat-resistant steel. The upper die descends from above. The press creates pressure. Aluminum flows, fills the die cavity. takes the shape of a piston. The process is called backward extrusion. Metal flows upward around the punch, forms the piston skirt. Pressure climbs to 10,000 tons. Forging time, 12 seconds. Metal densifies. Grains align along stress lines. This makes the piston strong. Forging increases strength 30% compared to casting. After forging, the press opens. Piston extracted. It's hot, 750 degrees. Weight, 66 pounds. Shape's close to final, but machining still needed. Heat treatment. The forged piston goes into the hardening furnace. Temperature, 986 degrees Fahrenheit. Hold time, 8 hours. Copper and magnesium dissolve into the aluminum. The structure becomes uniform. Then, rapid cooling in water. Water temperature, 68 degrees. Cooling rate, 180 degrees per second. Copper and magnesium don't have time to precipitate out. They're trapped in the lattice. Strengthening zones form. After quenching, the piston is soft. Hardness, 60 on the Brinell scale. Artificial aging is needed. The piston is heated again. Temperature, 374 degrees. Time, 16 hours. Copper and magnesium precipitate from the lattice as fine particles. They strengthen the aluminum. Hardness climbs to 135 on the Brinell scale. Strength reaches 65,000 pounds per square inch. Elongation, 10%. The piston is strong and ductile at the same time. Machining begins with the turning operation. The piston gets clamped into the chuck of a CNC lathe. The chuck diameter is 19.7 inches. Spindle speed is 300 revolutions per minute. The cutting tool is carbide, tungsten carbide. They machine the outer surface of the skirt. Final diameter is 11.02 inches. Tolerance, plus or minus 0.0008 inches. Skirt taper, 0.002 inches per inch of length. This compensates for thermal expansion. Cutting speed is 490 feet per minute. Feed rate is 0.008 inches per revolution. Depth of cut is 0.02 inches. They remove 0.28 inches from the diameter. Machining time is 20 minutes. The surface is smooth. Surface roughness is 63 micro-inches. Then they mill the ring grooves. 3 grooves. Width of the first is 0.16 inches. Second is 0.14. Third is 0.2 inches. Depth of the first is 0.31 inches. Milling cutter diameter is 4 inches. Spindle speed is 1200 revolutions per minute. Groove accuracy plus or minus 0.0004 inches. They're drilling the hole for the piston pin. Hole diameter, 4.33 inches. Depth, 7.87 inches. Carbide drill bit. Rotation speed, 500 revolutions per minute. Feed rate, 0.006 inches per revolution. Drilling time, 8 minutes. After drilling, reaming. The reamer brings the diameter to 4.3302 inches. Tolerance, plus 0.0004 inches, minus 0. Surface roughness, 0.315 thousandths of an inch. This is an interference fit for the bronze bushing. The bushing gets press fit with 10 tons of force. Interference, 0.0012 inches. They mill the oil channels. 2 channels, diameter 0.47 inches, running from the crown to the skirt. They carry oil away for cooling. They drill the oil jets. Diameter, 0.079 inches. 8 of them around the crown circumference. Oil sprays through them onto the inner surface. Cooling is critical. Crown temperature hits 662 degrees Fahrenheit. The oil carries the heat away. Machining the combustion chamber. The piston crown gets milled on a 5-axis machine. The combustion chamber has a complex shape. A toroidal cavity, diameter 7.1 inches. Depth 2 inches. Chamber volume 0.3 gallons. The shape's optimized for mixing fuel with air. Ball nose cutter, diameter 0.8 inches. Spindle speed 3,000 revolutions per minute. Tool path spirals from center to edge. Spiral pitch 0.02 inches. Machining time 40 minutes. Surface roughness 0.00016 inches. Then chamber polishing. Abrasive paste 3 micron grit. Polished with a felt wheel. Speed 1,000 revolutions per minute. Time 5 minutes. The polished surface prevents carbon buildup. Final operation, honing the skirt. Honing creates a crosshatch pattern of micro grooves. Angle 60 degrees. Groove depth 0.00012 inches. Width 0.0008 inches. These grooves retain the oil film, reduce friction. Honing time 10 minutes. Coatings and inspection. The crown gets a ceramic thermal barrier coating. Thickness 0.3 millimeters. Material yttria stabilized zirconia. Thermal conductivity 2 watts per meter Kelvin. That's 100 times less than aluminum. The coating drops the crown temperature by 100 degrees. Applied by plasma spray. Plasma temperature 10,000 degrees. Particle velocity 1,000 feet per second. The skirt gets a graphite coating, anti-friction. Thickness 0.015 millimeters. Cuts friction by 40%. Reduces wear at startup. Ring grooves get hard anodized. Hard anodization. Layer thickness 0.05 millimeters. Hardness 500 Vickers. Protection against ring wear. Every piston gets inspected. Diameter measured at 6 points. Laser micrometer. Accuracy 0.001 millimeters. Weight gets checked. Scale accurate to 1 gram. Tolerance plus or minus 5 grams. Weight variance in a set no more than 10 grams. For engine balancing. X-ray checks internal defects, cracks, porosity, inclusions. Rejection rate 0.5%. Finished piston weighs 51 pounds. Diameter 11 inches. Height 13.8 inches. It'll run 10,000 hours, 70 million cycles. Handle temperatures of 350 degrees. Pressure 185 bar. Speed 33 feet per second. That's how Caterpillar makes the biggest pistons. From aluminum ingot to a component that holds 9,000 horsepower. If this was interesting, hit that like button. Comment what engines you know. Subscribe. Here we show you how giants get made. Picture a metal that's everywhere in nature, yet remains one of the most expensive and difficult materials for industry to work with. That metal is titanium. It's abundant in the Earth's crust, but producing it is so labor-intensive, energy-hungry, and technologically finicky that the aviation industry literally fights for every quality pound. And that's not an exaggeration. Without titanium, there'd be no modern jet engines, no critical aircraft components, no landing gear parts, no structural elements where you need high strength, low weight, and corrosion resistance all at once. But the journey of titanium from black sand or ore concentrate to an aircraft part is remarkably far from conventional metallurgy. You can't just melt it down, reduce it with carbon, and pour it into a mold like steel or iron. Titanium is too reactive. It bonds with oxygen way too easily. It's too sensitive to contamination. And that's exactly why producing titanium for aviation isn't just mining and smelting. It's one of the most complex sequences of chemical and metallurgical operations in modern industry. In nature, titanium almost never occurs as pure metal. Industry extracts it from minerals, mainly rutile and ilmenite. Very often, these ores aren't mined in classic deep mines, but in what are called mineral sands, placer deposits that form along coastlines and in ancient sedimentary zones. This means the first stage of titanium production looks totally different from the typical picture of miners and mine shafts. Here, they might use dredges, excavators, washing systems, gravity and spiral separators that separate heavy minerals from lighter waste rock. But even after processing, what you have isn't metal yet. It's just titanium-bearing raw material. And this is where the main paradox kicks in. Titanium is extremely abundant, but extracting actual metallic titanium from its oxides is way harder than smelting many far rarer metals. That's exactly why titanium is expensive, not because it's rare in nature, but because turning ore into aviation-grade metal is brutally complex. The next stage is converting the ore into a chemical form from which pure metal can actually be extracted. For titanium, this is especially critical because the usual heat-based reduction doesn't work here. While iron or copper can be processed using relatively straightforward metallurgical methods, titanium is a different beast. Its oxide is too stable, and the metal itself, at high temperatures, binds too aggressively with oxygen, nitrogen, and carbon. So industry takes an indirect route. Titanium feedstock is first converted into titanium tetrachloride, a volatile chemical compound that can then be purified. To do this, the concentrate undergoes high-temperature chlorination in the presence of a reducing agent, and then the resulting product is sent for purification. The key advantage of this approach is that titanium tetrachloride can be purified through distillation, removing a whole range of unwanted impurities. Essentially, this is the moment when rough mineralogy transforms into chemically controlled feedstock for the metal to come. And it's at this stage that it becomes clear. Titanium production isn't classic smelting. It's a chemical, metallurgical process with extremely tight purity requirement. Once the purified titanium tetrachloride is ready, one of the industry's most critical processes kicks in, the Kroll process. This is the fundamental industrial technology that makes modern mass production of titanium for aviation, aerospace, and other high-tech fields even possible. Here's how it works. Purified titanium tetrachloride reacts with molten magnesium inside a sealed reactor. The result? The metal breaks free from chlorine and forms what's called titanium sponge. This isn't a solid ingot or finished semi-product yet. It's a porous, brittle metallic mass that looks like hardened porous rock. After the reaction, leftover magnesium and byproducts get removed. Then the sponge is sorted, crushed, and prepped for the next stage. At first glance, you might think the sponge is almost finished metal, but really, it's only halfway through a long journey. Aviation doesn't just need titanium. It needs material with precise chemical composition, high uniformity, and predictable behavior under stress. So next, this sponge still has to be transformed into a full-fledged structural metal. The next major stage is remelting the titanium sponge into a dense, homogeneous ingot. And this is where production gets especially tricky again. Molten titanium aggressively absorbs oxygen, nitrogen, and other impurities from the surrounding environment. Even slight contamination can make the metal brittle and unsuitable for critical aircraft components. That's exactly why titanium remelting doesn't happen in a regular shop floor atmosphere. It's done in a vacuum or a controlled inert environment. One of the key methods is vacuum arc remelting. For this process, they form a consumable electrode from titanium sponge, alloying additives, and sometimes a portion of quality scrap returns. Then, this electrode is gradually melted by an electric arc, and the metal collects drop by drop in a water-cooled mold, forming an ingot. For critically important aerospace applications, a single remelt like this often isn't enough, so the metal may go through double or even triple remelting to achieve maximum structural uniformity, stable composition, and the absolute minimum number of defects. But aviation doesn't just need pure titanium. In most cases, the foundation is special titanium alloys, and the most famous of these is Ti6Al4V, also known as Grade 5. In this material, titanium is alloyed with aluminum and vanadium to achieve a combination of properties that's practically impossible to replicate in many other metals. This alloy is noticeably lighter than steel, yet it has very high specific strength, good fatigue resistance, and outstanding corrosion resistance. That's exactly why it's used in compressor discs and blades of aircraft engines, in landing gear components, structural load-bearing elements of the aircraft, and other assemblies where every pound matters. But for titanium to become a true aerospace material, it's not enough to just melt it into an ingot. What follows is forging, rolling, heat treatment, microstructure control, and mechanical property verification. In other words, aerospace-grade titanium isn't just a metal, it's an entire series of carefully sequenced operations, each one affecting the final reliability of a part that will later operate under enormous loads. This is where it becomes clear why titanium is so expensive. First, production isn't continuous, it's largely cyclical. The Kroll process is slow and energy-intensive. It requires magnesium, chlorine, sealed reactors, and complex purification afterward. Second, almost every hot stage demands a vacuum or inert atmosphere. Why? Because the metal reacts too aggressively with oxygen. Third, titanium itself is a nightmare to machine. It has low thermal conductivity. Heat doesn't escape into the chips. Instead, it concentrates on the cutting tool. This accelerates tool wear, slows down machining speeds, and drives up the cost of every finished part. On top of that, titanium semi-finished products require extremely precise control of structure and chemistry, and tolerances in aviation are far tighter than in mass industry. The bottom line? Titanium isn't expensive because it's rare in nature. It's expensive because the entire chain, from ore to aerospace-grade alloy, is extraordinarily complex, long, and sensitive to any deviation from the process. There's one more reason titanium is so valued specifically in aviation. It fits perfectly into the philosophy of modern engineering, where weight savings directly translate into efficiency gains. A lighter aircraft burns less fuel, carries more payload, and its engine and structural components operate in more favorable conditions. But titanium isn't a universal replacement for steel or aluminum. It's used where it truly justifies its cost, in hot sections, highly stressed components, corrosive environments, and parts where the combination of strength and low weight is critical. That's why titanium production for aviation isn't just metallurgy for the sake of metal. It's an industry where every step serves a single purpose: to create a material that will perform reliably in an aircraft at high speeds, under cyclic loads, vibrations, temperature swings, and with enormous responsibility for safety. When you look at titanium's entire journey, you're witnessing a nearly perfect example of modern high-tech manufacturing. First, heavy mineral sands or ore concentrates get separated from waste rock. Then, chemical processes transform the raw material into purified, volatile compounds. Next, through the Kroll process, they obtain porous titanium sponge. After that, it's remelted into ingots under vacuum, alloyed, structurally and chemically refined several times over, and only then transformed into semi-finished products and parts for aviation. In other words, titanium's journey is a path from dirty natural mineral to a material that can work inside a jet engine or an aircraft structural assembly. And perhaps that's where titanium's real power lies. It seems like just another element in Earth's crust, but actually becomes a true engineering marvel only after incredibly complex technological processing. That's why aviation-grade titanium isn't just a metal. It's the embodiment of how far industry can push when it needs the perfect balance of strength, lightness, durability, and reliability.
$1,300,000,000 meters of submarine internet cables have already been laid on the ocean floors. And every year, this length grows. Also, we can send a message, watch a video, or make a call across continents. Over 95% of all intercontinental internet traffic passes through them every day. Stretched through the depths, they cross volcanic ridges, encounter sharks, ships, and even geopolitics. How are these gigantic infrastructures created? Who designs the routes? How are they laid on the seabed at depths of over 26,000 feet? And what happens when a cable is damaged?
For the internet to cross oceans, a cable is needed that can withstand pressure, salt water, marine life, and decades of operation without repair. It all starts with the central core, a copper or aluminum conductor, through which the main signal travels. Large ingots of purified metal are melted and passed through drawing machines, which repeatedly pull the material through narrowing dies, reducing the diameter to a few millimeters. At this stage, a perfectly round cross-section is formed, one that has no microcracks or air pockets. After drawing, the wire undergoes heat treatment. It is heated to a precisely set temperature to relieve internal stress and make it more flexible. Then it is cleaned of oxides, often by a chemical method, or using abrasive rollers.
The output is a shiny, smooth, almost flawless wire. It is checked automatically for diameter, resistance, flexibility, and surface purity. The wire must withstand kilometers of bending and work without failure, even at depths of several thousand feet. Depending on the type of cable, the wire is either used as a single solid conductor or is twisted from several thinner strands, which increases flexibility and protection against breakage. Once the copper or aluminum conductor is ready, it is immediately fed into an extrusion line, a long machine resembling a tunnel. Inside, polyethylene heated to 482 degrees Fahrenheit, which melts into a thick, viscous cream. The conductor moves along a conveyor and enters the extruder head, where the molten polymer precisely and evenly flows around the metal, like a second body. Every millisecond is important here. Too slow, and drips will form. Too fast, the polyethylene won't have time to adhere. Immediately after this, the cable enters a bath of cooling water, where the polyethylene layer quickly solidifies, tightly enveloping the conductor. The entire surface must be smooth, without a single bubble or crack. This is the first line of defense against moisture. After cooling, inspection. Lasers measure the insulation thickness, and cameras check the surface. If anything is even slightly off, the cable is cut and reprocessed. The next stage is the application of a hydrophobic gel, which acts as an invisible protector. This thick, viscous compound fills all the voids inside the cable, envelops the optical fibers, and creates an internal shield against moisture. In a special chamber, the cable passes through a system of nozzles or rotating heads that evenly apply the gel to the central part and in the space between the fiber elements. The gel resembles a transparent lubricant. It doesn't dry out, freeze, or dissolve in water, even at a depth of 26,000 feet under a pressure of hundreds of atmospheres. Its main property is to repel water. If the cable sheath is ever breached, the gel instantly spreads and prevents moisture from penetrating inside, not letting it reach the sensitive fibers. At this stage, it's also important that there isn't too much gel, otherwise it complicates the further laying of layers, and not too little. Then the protection efficiency drops. Computers precisely regulate the dosage, and operators visually check the filling and uniformity. After application, a short cooling and stabilization. Now the cable is ready to receive its optical heart, the fiber threads that transmit light from one continent to another. These fibers, usually from 4 to 12 of them, are first grouped into modules. Each module is a flexible capsule with several fibers inside, providing additional protection. The modules are very carefully arranged in a spiral around the central conductor. This configuration allows the fibers to bend without tension, especially during winding and laying the cable at sea. To keep the fibers in place, they are fixed in a bedding of gel that was applied earlier. There is no glue, only a tight fit and a flexible structure. It's important that no fiber crosses another, breaks, or shifts from its place. The work is almost like jewelry making, although it's done on a conveyor. Afterward, a continuity check of each fiber. A laser beam is sent through them. Even a microcrack or a bend will cause a failure, and the fiber won't pass inspection. If everything is fine, the structure moves on to the next stage, additional insulation and reinforcement. First, an additional polymer layer is applied over the optical fiber structure. Often it's high-density polyethylene, or another flexible waterproof material. It protects against mechanical damage, friction, and moisture. This is again done in an extruder, similar to the one where the first insulation layer was applied. The cable passes through molten polymer and immediately enters a cooling bath.
After cooling, the cable enters the steel wire braiding section. Machines evenly lay steel rods or tapes in a spiral around the already insulated core. In shallow water areas, this armor is thicker to protect against anchors, fishing nets, and shark teeth. At depth, the armor is thinner or absent altogether. After reinforcement, another outer polymer sheath may be added, which seals the entire structure. Operators carefully inspect the cable surface, checking for uniform thickness, no abrasions, burrs, cracks, or armor misalignments. Then, automated tests. Lasers scan the thickness. Cameras capture every millimeter. Light pulses are sent through the fibers again. The signal must pass without delays or losses. If a defect is found at this stage, it is cut out and both ends are joined using a special technology, creating a sealed splice joint.
After inspection, the cable enters the marking section. Here, information about the batch, production date, cable type, and its purpose is printed on the outer sheath, often every few feet, so it's easy to identify the cable even during laying on the seabed. And finally, winding onto spools. These are giant drums with a diameter of up to 13 or 16 feet, which can hold up to 8,200 feet of cable. Each turn must lie flat, without twists, and with uniform tension. Automatic systems regulate the speed and tension force, and operators monitor each stage. If the cable is intended for installation at sea, the drums are immediately sent to ships, where they are installed on the deck. If not, they're stored in special warehouses with humidity control, because even minor corrosion can be fatal.
Picture this: 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, zero coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads, the first vehicle in history made from steel with a zero carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal in blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green. The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math, around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution. And it started in cold Sweden, in the city of Luleå, above the Arctic Circle.
2016, three Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane: replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen, pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks, the first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 green steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's Voest-Alpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology.
Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still.
Another advantage of hydrogen metallurgy, it's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well.
Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.
You're holding $100 in your hand, a green piece of paper with Franklin's face on it. Light, thin, looks ordinary, but it's not paper, and it's not ordinary. This bill was printed in a building guarded better than the Pentagon. Cameras everywhere, motion sensors, armed security. Getting in there is harder than getting into Fort Knox. The paper for it was made using a secret formula: 75% cotton. 5 people in the world know the formula. Printed 3 times. Each time with different inks. Each time with precision down to a micron. One wrong stroke, and the bill is counterfeit. Checked by machines, every millimeter scanned. Rejects burned immediately. Not even one bad bill gets out. Because if it makes it outside, someone could forge it. This piece of paper is protected better than a vault in a bank. Watch till the end, you'll learn how money is printed. And you'll never look at a dollar as just a simple piece of paper again. Texas, cotton fields stretching to the horizon, heat pushing 100 degrees, white cotton bolls bursting on the bushes. Combines harvesting the crop, but not all cotton makes the cut for money. Only the longest fibers. White, strong, hand-selected, shipped to the factory, Massachusetts, town of Dalton, Crane Currency Facility. They've been making paper for dollars since 1779. Nobody else in the world has the rights. The grounds are guarded around the clock. Airport-level security screening. Cameras in every corner. Cotton gets mixed with linen. Boiled in massive vats. Water added. Creates a white pulp. Rolled into thin sheets. During the rolling, red and blue fibers get woven in. Randomly. Chaotically. Impossible to replicate the pattern. First line of defense. Then a security strip gets embedded. Thin metallic thread, glows under ultraviolet light. Water pressed out, dried. Cut into large sheets. Every sheet inspected against the light. Checking for defects. One air bubble. Sheet gets rejected. Finished paper gets packaged. Transported under convoy, armed guards, armored truck. Because if someone steals this paper, they can print real money. Washington, D.C. A building with no signs. Gray, nondescript. Inside, they print money. Bureau of Engraving and Printing. Security level like a military base. Metal detectors, retinal scanners, fingerprints. Even employees can't enter without triple verification. Cell phones banned. Cameras banned. Any recording devices confiscated. Inside, printing presses the size of a bus. Each one costs $10 million. Running around the clock. Sound like a jet taking off. Paper loaded in stacks. 32 sheets per stack. Each sheet will print 32 bills. First pass, background printing. Green patterns, fine lines. Hand-drawn by engravers, for months. One mistake, start over. Lines so fine they're invisible to the naked eye. That's the second anti-counterfeiting measure. Special ink. Formula classified. Made at a different facility. Under the same level of control. Sheets pass through the printing cylinder. Come out green. Wet. Dried under infrared lamps. Every sheet inspected. Sensors scan color, density, line alignment. Precision. 1/100th of a millimeter. Thinner than a human hair. Second pass. Intaglio printing. The most important one. Franklin's portrait, the numbers, the text, all of it printed under massive pressure. 3 tons per square centimeter. The ink gets pressed into the paper. Run your finger across it, you feel the texture. That's the main security feature. Impossible to fake. Regular printers can't do this, even professional ones. You need a special machine. There are 10 of them in the world, and they're all here. The printing cylinder is covered in microscopic grooves. The design is laser engraved. Precision, 5 microns. That's 10 times thinner than a human hair. The cylinders get replaced every year. The old ones are destroyed, melted down, turned into scrap metal. So nobody can recover the design. Sheets pass through the machine. Come out with Franklin's portrait. Sharp numbers, raised lettering. Another inspection. Machines scan every detail, compare it to the standard. If even 1 pixel is off, the sheet gets rejected. Rejects are set aside separately. Shredded at the end of the day. Burned. The ash dissolved in acid. Even the ash from dollars can't just be thrown away. Third pass, serial numbers. Every bill gets a unique code, 11 digits and letters. This combination doesn't exist anywhere else in the world. Printed in green ink, right side and left side. The numbers must match perfectly. The machine checks. If left and right don't match, rejected. Right then, they print the Treasury seal, green circle, and the Federal Reserve Bank seal, black. The letter shows which bank issued the bill. All of this happens in 3 seconds. The sheet runs through the machine, comes out with numbers and seals. Final inspection, the toughest one. Machines scan the bills under ultraviolet light, under infrared light, under magnification. They check 15 parameters: color, texture, security strip, watermark, line alignment, ink density, size, centering, numbers. Any deviation, rejected. Rejection rate, 3%. Out of every 1,000 bills, 30 get destroyed. Good sheets go to cutting. The rest, into the shredder. Cuts into individual bills. Precision, 1. Cuts into individual bills. Precision, 1/10 of a millimeter. If even one bill is cut crooked, the entire sheet is scrapped. Bills drop into a tray. A robot picks them up, counts them. 100 bills per stack. Wraps them in paper. 100 stacks per block. $10,000 in a single block. Blocks get wrapped in film, sealed, stamped with the date. Serial number, quantity, loaded into safe containers. Metal ones. Locked with 3 separate locks. 3 different people hold the keys. One person can't open it. Containers get loaded into an armored truck. Armed guards. 2 escort vehicles. Driven to the Federal Reserve Bank. There they're unloaded into the vault. Underground. Walls 3 feet thick. Steel reinforced concrete. The bills sit and wait until some bank requests them. Then they're pulled out. Counted, packaged, shipped off. Your local bank orders fresh bills. The request goes to the Federal Reserve. From there, they ship a container. Again, under guard. Brink's armored truck. 2 armed guards. GPS tracker, dispatch communication. Any route deviation triggers an alarm. They arrive at the bank, unload into the vault, check the seals. Open the container, count everything. By hand and by machine. The amount must match to the cent. Some bills go into ATMs. An operator loads the cassettes, $4,000 in one cassette. Inserts it into the ATM. Closes it up, ATM's ready. You walk up, insert your card, enter your PIN, request $100. Inside, rollers activate. Grab one bill, sensors check it. If the bill's wrinkled or torn, the ATM won't dispense it. Takes the next one, feeds it through the slot. You grab it, fold it into your wallet, and walk away. Never thinking about the journey that piece of paper took. From a cotton field in Texas to your wallet. Secret paper, triple printing, 15 inspections, armed guards at every stage. Now you know. This bill isn't just paper. It's the most protected document in the world. It was printed by people who passed security clearances, working on machines worth $10 million, under cameras and sensors. Any mistake, and the bill is destroyed, burned, dissolved in acid. Because even a defective bill in the wrong hands is a threat. Someone could study it, understand the technology, try to counterfeit it. That's why the security is so tight. You'll never look at a $100 bill like ordinary paper again, because now you know it has 300 years of technology encrypted in it. Red fibers in the paper are randomly placed. The security strip glows under ultraviolet light. Franklin's portrait is pressed under 3 tons of pressure. Microlines thinner than a hair. Serial numbers unique. This bill is impossible to counterfeit, even if you really try, because it wasn't made to be beautiful. It was made to protect money from counterfeiters, and it works. Every year, over 1,000 giant ships are sent for scrapping, each weighing up to 50,000 tons, nearly the length of 3 football fields. It's like dismantling an entire floating city with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster becomes inevitable. But here's the thing, that's not even the most surprising part. Inside each of these massive vessels lies something that turns scrapping into a genuine treasure hunt. Workers risk their lives amid plasma cutters and toxic fumes to extract these valuables. What exactly are they after? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone stays silent about? Stick around till the end. What you're about to discover will make you look at every ship in port with completely different eyes. This is the story of how steel giants die and new metal is born. Why is ship recycling important? The vessels we typically picture as massive floating megastructures can stretch nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for ocean travel and cargo transport. But beyond their massive scale, these ships have an incredibly complex internal structure. Hundreds of miles of cables, pipelines, shafts, and various safety and comfort systems, plus countless different components and mechanisms serving different functions. This entire architecture isn't just metal, it's a complex organism that needs to be very carefully and properly dismantled when a ship reaches the end of its service life. It's absolutely critical to properly remove all hazardous substances accumulated during its operation. These can include bioactive materials, toxic paints, fuel residues, oils, chemicals. If handled improperly, these substances can contaminate the ocean, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a disaster for nature. However, recycling these ocean giants has a very bright positive side. The metal the ship is made from is excellent and valuable raw material that can be recycled and returned to production. This metal is used to build houses, cars, construction structures, and even create new ships. This reduces the need for smelting new steel, saves energy and resources, and also cuts down on waste. Recycling metal from ships becomes a critical link in the closed loop of the modern industrial economy. Disposing of such massive objects also frees up ports where old vessels sit, making room for new, modern ships. The ship is brought to specialized ship graveyards, typically shorelines with shallow water or dedicated slipways. These locations aren't chosen randomly. Shallow shorelines allow easy beaching, where the vessel can be safely moored and dismantling can begin. Often these are small bays or beaches where the massive ship is deliberately run aground so it doesn't obstruct maritime traffic or damage port infrastructure. Slipways, on the other hand, are large platforms or specialized structures where the ship is positioned for land-based dismantling. They're equipped with everything needed for convenient and safe operations: crane equipment, metal cutting tools, waste removal systems. One of the specialists' primary task is ensuring environmental safety. After all, during its operational life, the ship accumulated many substances that could harm the environment if handled carelessly. We're not just talking about oil and fuel residue here, toxic paints and chemicals too. That's why the entire scrapping process kicks off with removing all that hazardous stuff. Fuel and oil get drained into special containers and hauled away for processing or disposal, keeping them out of the water and soil. Same goes for electronics and furniture. Anything that could potentially harm the environment gets pulled out first. This stage demands speed and extreme caution, so environmental regulations aren't violated. Once the ship's been cleared of all hazardous and everyday materials, the actual hull dismantling begins. And this is the toughest and most dangerous part. Using specialized plasma cutters and gas torches, massive steel structures get sliced into smaller pieces. It takes both handheld equipment and heavy machinery, cranes, lifts, specialized manipulators. Plasma cutting allows for incredibly precise, fast, and efficient separation of metal that'll later be melted down and recycled. The dismantling process itself happens sequentially, step by step, starting with the most difficult to reach or hazardous zones. Metal sheets, beams, decks, and internal bulkheads are carefully removed to avoid damaging structures that might still be needed for analysis or processing. The challenge is that these massive components are often unevenly positioned and may be under tension, and due to corrosion or hull deformation, sections can unexpectedly shift or collapse at any moment. Worker safety is also critically important. During plasma cutting, hot sparks and toxic fumes are generated, requiring workers to use special protective equipment, respirators, specialized clothing, and constant air quality monitoring. A small mistake or disregard for safety protocols can lead to serious injuries and accidents. That's why every step of the process is governed by strict safety protocols, and the entire facility is covered by fire suppression systems and medical support. Breaking down the hull and main steel structures of the ship is, without a doubt, an incredibly important and complex stage in scrapping a giant vessel. But once that massive chunk of work is done, the job isn't over. Up next, another huge phase that demands just as much attention and a certain level of skill, because it involves dismantling and sorting tons of smaller yet equally valuable and complex materials. One of the most massive and challenging processes is dealing with cables. A ship contains hundreds of miles of cable networks that power and connect all its systems. These are heavy-duty steel cables with plastic insulation, rubber, and maybe even non-ferrous metals mixed in. Cables don't just sit around at the recycling yard. They're carefully extracted, processed, and sorted. Separating the metal core from the insulation materials makes it possible to send pure copper or aluminum for remelting, while the insulation layer goes for processing as raw material for new polymers. Workers have to be really careful not to damage long cable sections, and they've got to follow safety protocols because of residual substances or rust. Another important category of materials is insulation materials that are glued to or fill the ship's walls, technical spaces, and pipelines. Insulation is often made from specialized materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After the insulation is extracted, it's sorted and sent to specialized facilities. Working with ventilation systems demands equal care. Ventilation ducts and units, used for air conditioning and circulation throughout different parts of the vessel, get dismantled and cleaned of dust, oil residue, and other substances. The metal components of these systems are typically high-quality material for remelting, while plastic or rubber often becomes raw material for new products. Special attention goes to water supply systems and sanitary installations. A ship carries complex shut-off mechanisms, piping, fittings, faucets, tanks, and other equipment. Pipe sections and equipment get carefully separated, cleaned of sediment, oil, and other contaminants before being sent for remelting or appropriate processing. These materials can contain toxic substances, so their disposal or recycling follows strict protocols. Equally critical is dismantling equipment from the engine room. That's where you'll find engines, generators, pumping systems, turbines, and other complex machinery. Stuff that's usually heavy as hell and packed with metals, including non-ferrous ones. This equipment mostly gets repaired and reused or broken down into parts, some of which are recycled. In certain cases, engines are even sold as used spare parts, dodging the scrap heap entirely. Furniture, appliances, lighting, and other interior items from the ship don't just get tossed either. They're removed and sorted. Wooden, metal, or plastic components go through separate recycling or disposal processes. Sometimes, if furniture's in decent shape, it gets sold for reuse. And just like that, after going from floating city to thousands of tons of sorted raw materials, the giant ship gets a second life in new homes, cars, and even new vessels. This is the story of how the death of a steel giant becomes the beginning of a new life for millions of tons of metal.
Every year, thousands of quarries crush millions of tons of rock. The biggest dragline in history, Big Muskie, weighed 13,500 tons. That's like 10,000 cars. But the real star isn't the machine itself, it's the teeth. Parts weighing up to 150 pounds that bite into granite every single day. How does ordinary steel transform into nearly impenetrable armor? Today you'll see the complete cycle, from molten metal to a tooth that survives 50,000 impacts. If you want to see how they make the fangs of giants, subscribe to the channel. Here we show you the operations that tear into the earth. Big Muskie weighed 29,779,800 pounds. The bucket could fit 2 buses side by side. Bucket capacity, 4,300 cubic feet. 60 teeth on the bucket. Each tooth weighs 50 to 150 pounds. A tooth isn't just a chunk of iron, it's an engineering marvel that bites into granite day after day without wearing down. Teeth are made using 2 methods, casting and forging. Right now, you're seeing casting. Material: alloy steel with nickel and molybdenum. Molybdenum improves hardening, nickel provides toughness and corrosion resistance. Carbon content from 0.33 to 0.5%. That's high carbon steel. It's hard after quenching. Steel melts in an electric arc furnace. Temperature: 2,692 degrees Fahrenheit. 3 graphite electrodes. Arc between electrodes and metal. Power: 10 megawatts. Furnace holds 20 tons. Melting time: 2 hours. Steel gets purified. Sulfur removed with lime. Phosphorus by oxidation. Then the metal stirred in an argon-oxygen deoxidizer. Argon blown in from below. Pressure: 73 psi. Flow rate: 79 gallons per minute. Argon bubbles rise. Mix the melt. Carry gases to the surface. Hydrogen content drops from 10 to 2 parts per million. Oxygen from 80 to 20. Low gas content is critical. Gas bubbles become cracks. Finished steel pours into a ladle. Ladle lined with refractory. Melt temperature: 2,649 degrees Fahrenheit. Ladle holds 2,000 pounds, enough for 20 to 30 teeth. Investment casting. First, they make a wax model. Wax melts at 158 degrees Fahrenheit. Pour it into the die. Cool it down. You get a wax copy of the tooth. Accuracy down to a few thousandths of an inch. Models are assembled onto a sprue tree, 5 to 10 teeth per tree. The tree gets dipped in ceramic slurry. The slurry is fine zirconium powder in colloidal silica, particle size about 2/10,000ths of an inch. Dip the tree, pull it out. Coat with coarse zirconium sand, grit size about 1/100th of an inch. Dry it. Repeat 7 to 10 times. Each layer about 1/16th inch thick. Final shell thickness roughly 1/2 inch. The shell withstands 2,800 degrees Fahrenheit. That's the steel pouring temperature. They melt out the wax. Heat the mold to 1,500 degrees. Wax melts, flows out through openings, leaves behind a cavity that's the exact shape of the tooth. Pouring. The mold heats up to 1,800 degrees Fahrenheit. A hot mold means less thermal shock during the pour. A crane brings the steel ladle into position. The steel's at 2,650 degrees. It glows bright orange. They pour fast but carefully. Pour rate is 4 pounds per second. Air bubbles will kill the part. Metal fills the mold from bottom to top, pushes air out through the top. After pouring, they don't touch the mold. Cooling is slow, 8 to 12 hours to reach room temperature. Fast cooling means cracks. Slow means proper structure. Once it cools down, they break the shell. Sandblasting machine. Pressure at 120 psi. The sand is corundum, grit size 20 micrometers. The ceramic cracks and crumbles away. Underneath, a gray cast tooth. Surface is rough, ceramic remnants in the recesses. But the form is precise. Deviation from the blueprint is less than a millimeter. Heat treatment. First stage, normalizing. The teeth get loaded into the furnace. Temperature, 1920 to 2070 degrees Fahrenheit. Hold time, 10 hours. At this temperature, the steel recrystallizes. Large grains break down into smaller ones. The structure becomes uniform. It's like muscle recovery after a workout. The metal gets stronger and more flexible. Air cooling. Cooling rate, 90 degrees per hour. Second stage, hardening. Heat to 1,870 degrees. Hold time, 2 hours. Then rapid cooling in oil. Oil temperature, 140 degrees. Cooling rate, 540 degrees per second. The structure transforms into martensite. That's a needle-like crystal lattice, extremely hard. Hardness after quenching, 59 to 63 on the Rockwell C scale. That's harder than a file. But hardened steel is brittle as glass. One strike, crack. That's why there's a third stage, tempering. Heat to 400 to 500 degrees Fahrenheit. Hold for 4 hours. This relieves internal stresses, adds flexibility. Hardness drops to 48 to 52 units. Perfect balance. Hard enough not to wear down, flexible enough not to break. Some manufacturers use induction hardening. The tooth gets placed in an inductor. Current frequency 400 kHz. Power 100 kilowatts. The surface heats up in 3 seconds to 2,700 degrees Fahrenheit. Heating depth 0.04 to 0.08 inches. Immediately cooled with water. Pressure 145 pounds per square inch. Flow rate 26 gallons per minute. The surface hardens. The core stays soft. Surface hardness 58 to 63 units. Hardened layer depth 0.05 inches. Quality control. Every tooth gets checked with ultrasound. The probe generates waves at 5 MHz. Waves pass through the metal, bounce back off defects. A crack just 0.2 inches wide, rejected. They check hardness with a Rockwell tester. A diamond cone presses down with 330 pounds of force. They measure the depth of the indent. Below 48 or above 52, rejected. Too soft, it'll wear out fast. Too hard, it'll crack. The teeth get ground down. Grinding wheel made of aluminum oxide, 80 grit. Speed of 67 miles per hour. Takes off the rough spots from casting. Surface roughness drops from 0.001 inches to 0.00012 inches. Smooth surface holds up better against wear. Rough spots wear down faster. Marking. Every tooth gets a number. Laser engraving. Laser power 50 watts. Engraving depth 0.004 inches. The number shows the batch, date, and specs. Testing. One tooth from the batch gets sent to destruction. A hydraulic hammer strikes with a force of 1,000 pounds. Impact every 2 seconds. They count cycles until failure. A quality tooth withstands 50,000 strikes. Wear test. The tooth gets abraded. Quartz sand with 500 micrometer grain size. 5-bar pressure. 100 hours. That's equivalent to 1,000 hours of operation. The best teeth lose less than 0.5% of their weight. Production numbers. A big dragline, bucket holds 4,300 cubic feet, 60 teeth on the bucket. Each weighs 66 to 150 pounds. Teeth get replaced every 3 to 6 months. One dragline wears through 80 to 120 teeth per year. Hundreds of draglines operate worldwide. 50 large machines in U.S. coal mines alone. Tens of thousands of teeth produced annually. One tooth costs $1,000 to $3,000. 60 teeth per bucket, $180,000 just for consumables. Replace twice a year. That's why every tooth must be perfect. The economics of mining depend on the reliability of these steel fangs. That's how dragline teeth are made. From molten steel to a part that chews through granite. If this was interesting, hit that like button. Write which quarries you've seen. Subscribe. We show how giants are made. This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them. But today, I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it, and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, it looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet. Heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling. like the metal reluctantly gives in. I'm standing nearby, and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn, and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time, until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a whole section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the hull starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too. Several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next, so stick around. It's gonna be good. The cylinder block of a freight locomotive weighs 50 tons. 4 meters long, 2 meters wide, 5 feet tall. It's a single cast iron casting, 16 cylinders, 11 inches in diameter, an engine producing 4,500 horsepower, pulls a 5,000-ton train through the Colorado mountains and Nevada deserts without stopping. How do you cast the heart of such a monster? Today, you'll see the complete cycle at the Wabtec plant in Pennsylvania, from molding sand to a block with tolerances measured in micrometers. If you want to see how they make the engine that moves America, subscribe to the channel. Here, we show the manufacturing that keeps the world running. Molding sand. Silica sand, grain size 0.08 to 0.16 inches, 50 to 70 grit on the AFS scale. Mix with phenol formaldehyde resin at 3% of sand weight. Add hardener, sulfuric acid ester, at 0.5% concentration. The resin binds the grains. When cured, forms a structure with compressive strength of 435 pounds per square inch. The mold must withstand contact with molten cast iron at 2,460 degrees Fahrenheit. If it cracks, 33,000 pounds of metal spills onto the floor. Mix in edge runners. Time, 8 minutes. Moisture content of finished mix, 4%. Temperature, 72 degrees. Mix is ready. They make the mold in a pit measuring 16 feet by 10 feet by 6.5 feet deep. They lay the mixture in layers of 8 inches. They compact it with a pneumatic tamper. Air pressure 90 pounds per square inch, 300 blows per minute. Density of the compacted sand 100 pounds per cubic foot. They install the cores. Cores are sand inserts that form the cavities, oil channels, water jackets, piston chambers. 120 cores per block, each one made separately. Sand with quick hardening resin blown into the tooling at 115 pounds per square inch. The resin hardens in 30 seconds. They extract the core, check it with calipers, tolerance plus or minus 1/25 of an inch. They install them in the mold per the drawing. Installation accuracy plus or minus 1/12 of an inch. An incorrectly installed core creates a defect, shows up after machining, or in operation. They close the mold with the upper half, secured by 24 clamps, 10 tons of clamping force each. The mold is ready for pouring. They melt cast iron in an induction furnace with a 20-ton capacity. They load pig iron grade SCH25, carbon 3.4%, silicon 2.2, manganese 0.8, sulfur 0.12, phosphorus 0.2. They add alloying elements. Nickel 1% for strength, chromium 0.5 for hardness, molybdenum 0.3 for heat resistance. Furnace power 3 megawatts. Melting time 2 hours. Melting point 2,190 degrees Fahrenheit. They superheat to 2,462. They take a sample, analyze it with a spectrometer. Carbon plus or minus 0.1%. Silicon plus or minus 0.15. Composition confirmed. They begin pouring. The metal pours into a ladle that holds 18 tons. The ladle's lined with fire brick, 8 inches thick. Withstands temperatures of 2,700 degrees. A crane rated for 100 tons delivers it. They open the stopper. Metal flows into the pouring basin. Orange-white. Brightness hits 10,000 candelas per square meter. Don't look without protection. Pour rates 110 pounds per second. Pouring 15 tons takes 5 minutes. Can't stop. If you do, the metal freezes unevenly. You get cold joints, cold cracks, internal stresses. The blocks scrap. Metal fills the mold from bottom to top. Forces air out through ventilation channels 3/4 of an inch across. The pour's continuous. Mold's full. They pull the ladle back. Metal cools. Cooling 3 weeks, 21 days, 504 hours. Can't rush it, otherwise thermal stress. Micro cracks. Uneven structure. Outside looks fine. Under load, the stresses surface. Block cracks. They install 12 temperature sensors. Monitor the gradient. Difference between center and surface no more than 90 degrees Fahrenheit. First day temperature drops from 2400 to 1470. Rate 36 degrees per hour. Second day from 1470 to 930. Rate 22 degrees per hour. After a week, 212 degrees. After 3 weeks, room temperature, 72 degrees. They break the mold. Sand falls away. Clean it with shot blasting. Steel shot diameter, 0.04 inches. Pressure, 87 psi. Shot velocity, 230 feet per second. Cleaning 2 hours. Removes sand, scale, flash. Surface clean. Machining. Block on a CNC gantry mill. Work envelope 16 by 10 by 6.5 feet. Milling the datum surfaces. Bottom plane is the reference. Cutter 16 inches in diameter. Running at 300 revolutions per minute. Feed rate 20 inches per minute. Depth of cut 0.2 inches. Removing 1.25 inches of stock. Flatness plus or minus 0.002 inches per foot. Check it with a laser level. Boring the cylinder holes. 16 cylinders in a V at 45 degrees. Diameter 11 inches. Tolerance plus 0.0008 minus 0. Boring head set to 11.02 inches. Cutting speed 400 feet per minute. Feed point 0.004 inches per revolution. Depth 0.008 inches per pass. Final diameter 11.008 inches. Surface finish 63 microinches. One micrometer, 1/1000th of a millimeter. A human hair is 70 micrometers. The tolerance on the cylinder is 35 times thinner than a hair. The piston moves at 1,000 RPM. The clearance between piston and cylinder is 0.1 millimeter. More, gases blow by, compression drops, the engine loses power, burns oil. Less, the piston seizes. One correct value, deviation is not allowed. Every cylinder is measured with a bore gauge, 3-point, accuracy 0.001 millimeter. 3 sections along the height, 4 positions around the circumference, 12 measurements per cylinder. Shop temperature is 20 degrees plus or minus 1. Humidity 50%. Metal expands. 1 degree changes the dimension by 0.012 millimeters. Climate control is mandatory. They machine the crankshaft bearing surfaces, diameter 150 millimeters. Tolerance plus or minus 0.015. Holes for the camshaft. Mating surfaces for the heads. Full cycle 4 weeks. 28 days. 672 hours of machine time. A block weighing 55 tons. 13 feet long. 16 perfect cylinders. Miles of internal passages. Tolerances in micrometers. Ships to assembly. They install a 7,000-pound crankshaft, 16 pistons at 44 pounds each, cylinder heads, turbocharger, fuel injection system. 3 months later, the engine's ready. 4,500 horsepower, 15,000 pound-feet of torque, bolted to a locomotive. That locomotive pulls 120 cars, 11 million pounds of cargo, 60 miles per hour, through the Colorado mountains, across the Nevada desert, non-stop for years, for decades. And it all started with sand and a ladle of molten iron. That's how they make locomotive engine blocks, from casting to micrometric precision. If you're interested, hit like, drop a comment with engines you know, subscribe. We show you how giants are made. If you want to see what the industrial edge of the world looks like, come to Ecatepec. This suburb of Mexico City won't greet you with mariachis or cocktails on the beach. Here, the air is thick with exhaust fumes from old Volkswagen Beetles, and the mountains all around are shrouded in gray smog. But it's right here, among the dusty streets and endless chaos, that what Mexicans call their quiet revolution is happening. I'm standing at the gates of the Granutech factory. There's a pebble stuck in my right shoe, and in my mouth, the aftertaste of cheap pork tacos and dust. But ahead lies a black hell that's becoming this country's salvation. Mexico has a problem. Nope, scratch that. Mexico is facing a catastrophe. Every year, over 40 million tires get dumped here. Most end up in canyons, rivers, or just vacant lots, where they're burned, poisoning the air with dioxins. For Mexico City, a city already choking in its own basin, this is like slow poison. But there's another curse: the roads. In Mexico City, they're not just bad, they're midge. Thanks to constant earthquakes, soil subsidence, and tropical downpours, the asphalt here cracks faster than you can say gracias. Traditional bitumen gets brittle under the scorching high-altitude sun and washes away with the first rain. We decided to cross these two problems so they'd destroy each other, Carlos tells me, an engineer at the plant wiping sweat from his brow with an oil-stained hand. His eyes shine with pride, and I get why. We step inside. There's none of the sterility of American labs here. This place thrums with raw energy. Stage 1. Intake. Massive trucks, rusted and beaten down by life, dump thousands of tires right into a dirty yard. It's a depressing sight. Whole mountains of black rubber, reeking of sun-scorched burn. But the second they hit the conveyor, the magic begins. The Granutech shredders are monsters. They don't just cut, they tear. The sound's like a giant iron beast chewing bones. Vibration comes up through the floor, hammers your legs, makes your teeth rattle. There's no room for conversation here. We're communicating with hand signals. I watch a tire from a massive truck get shredded into ragged chunks in seconds. Here, unlike those sterile European factories, you see every drop of the worker's sweat. They're hand sorting whatever the magnets missed. It's dirty, heavy, honest work. The dust is so thick that sunlight cuts through it in yellow beams. We move to the fine grinding zone. Here, the rubber passes through a cascade of mills, getting finer and finer until it becomes rubber flour. This is the secret ingredient. Carlos grabs a handful of this black crumble and holds it out to me. It's warm, almost hot. "This isn't trash," he shouts in my ear. "This is flexibility. This is what keeps the asphalt from cracking when the ground under Mexico City shakes again." Mexicans are proud of this technology, and they have every right to be. Roads with added old tires last 3 times longer. They're not afraid of water because rubber repels moisture, preventing it from seeping into the pores and destroying the foundation. Plus, these roads are way quieter. Mexico City is one of the noisiest cities on the planet, and every decibel that the rubber highway absorbs is a blessing. If the shredder is the brute force of the Granutech plant, then the bitumen modification shop is its devious and dangerous brain. We leave the noisy yard and climb iron staircases to a platform housing gigantic mixing tanks. Here, the air changes. Instead of dry rubber dust, your lungs fill with a heavy, oily mist. It's the smell of hot bitumen mixed with the sweetish scent of heated polymers. Rising from the center of the platform is the reactor, a massive steel thermos where real alchemy happens. Temperature here holds steady at 360 degrees Fahrenheit. This is the critical threshold. Drop below it and the reaction won't start. Go above it and the bitumen will rapidly oxidize and lose its properties. I watch as an automated auger begins feeding that same black flour, fine rubber crumb no bigger than a 32nd of an inch, into the scorching night black bitumen. The moment the crumb touches the molten liquid, a physicochemical marvel begins. You can't see it with your eyes, but the sensors on the monitor show it. The viscosity of the mixture starts climbing fast. The rubber doesn't simply melt because the rubber in tires is vulcanized. It can't just melt like ice. Instead, adsorption happens. The rubber particles start drinking the light petroleum fractions from the asphalt. A rubber particle swells to 2 or 3 times its original volume. It balloons up, becoming soft and elastic, a gel-like structure. Inside the reactor, high-speed mixers are working, literally grinding this swollen rubber into the asphalt structure. This isn't 2 separate things anymore. This is modified binder. "Watch the gauge," Carlos shouts, pointing at the instrument. "Pressure's climbing because the mix is getting thicker than honey." At the molecular level, devulcanization is happening. Some of the sulfur bonds in the rubber break down, and the polymer chains of the rubber intertwine with the asphalt molecules. They create a new network, a kind of reinforcement at the micro level. This network is the secret to permanence. Now, let's compare. Regular asphalt? It's rocks glued together with pure bitumen. Under Mexico City's intense sun, it softens. Then, at night, when it cools down, it hardens and becomes brittle. Over time, it turns into a dry shortbread cookie. All it takes is one heavy truck rolling over that surface and microcracks appear. Water gets in, freezes, or just washes away the base, and voila! You've got another pothole where your road used to be. Granitec's rubber asphalt works like a tough rubber tile. When a truck presses down on this asphalt, it doesn't crack. It deforms and, here's the key, bounces back to its original shape. That's called elastic recovery. We walk up to the discharge valve, where Carlos draws some of the finished mix into a metal container for testing. As it cools slightly, he stretches it like rubber. Regular bitumen would just tear apart, but this one pulls into long strands, bounces back, and retracts again. Right now, before our eyes, tons of this black mass pour into the dump truck bed. The temperature's still holding around 320 degrees. The mix smells like power and progress. This truck's heading to the outskirts of Ecatepec, where tomorrow morning, Mexicans will drive to work on a new road. A road that won't fear the Texas sun, torrential rains, or heavy buses. This is the real triumph of Granutec. We took the toughest trash, ran it through a 180-degree inferno, changed its chemical nature, and turned it into the foundation for safe travel. Here, on this platform, surrounded by steam and the thundering of iron, you get it. The future doesn't have to be clean and white. Sometimes it's black, sticky, and smells like hot rubber. If you found it fascinating how old tires transform into the roads of tomorrow, smash that like button on this video. Drop a comment if you know other amazing ways to recycle waste. And subscribe to the channel to keep discovering the technologies reshaping our world right now.
Steel cables were invented to replace ropes made from natural fibers. Ropes couldn't handle heavy loads. Chains were stronger but 10 times heavier. Steel cables solved both problems. Today, these cables hold up bridges, lift cranes, anchor oil platforms at depths of over half a mile. Diameter, up to 21 inches. Weight, 70 tons. Braking strength, 9,700 tons. That's the weight of 50,000 cars. How do you make a cable that won't break? Today, you'll see the complete process, from a steel rod just a fifth of an inch in diameter to a giant cable 900 feet long. If you want to see how thin wire transforms into a monster with a 10,000-ton braking strength, subscribe to the channel. Here we show you the industries that hold the world together. History. The modern steel cable was invented in 1834 by German engineer Wilhelm Albert. He developed it for coal mines. Hemp and manila grass ropes couldn't handle the job. The weight of coal in a cage? Over 3,000 pounds. Mine depth? Nearly 1,000 feet. Hemp rope broke from moisture and rubbing against shaft walls. Albert braided cable from steel wire. Wire diameter, just under 1/10 of an inch. 6 wires per strand. 6 strands around a core. Cable diameter, 3/4 of an inch. Strength, 5 times stronger than hemp. Lasted years instead of months. During the World War, steel cables anchored mines to the ocean floor. Deployment depth, up to 300 feet. Water pressure, 150 pounds per square inch. A cable just over an inch thick held a 600-pound mine, plus current and waves. Today, steel cables are everywhere. Cranes, elevators, suspension bridges, drilling rigs, ski lifts. Wire drawing, it all starts with rod, a steel wire 5.5 millimeters in diameter. The rod is made from grade 70 to 80 steel. Carbon content, 0.7 to 0.8%. Manganese, 0.6%. This is high carbon steel, hard and strong. The rod unwinds from a coil weighing 2 tons. It's pulled through a drawing mill. This is a series of dies with holes of decreasing diameter. First die, diameter 4.8 millimeters. Second, 4.4. Third, 4.0. Fourth, 3.6. Fifth, 3.2. Sixth, 2.8. Seventh, 2.4. Eighth, 2 millimeters. 8 passes total. Each pass reduces the diameter by 10 to 15%. Between the dies are pulling drums. Drum diameter, 500 millimeters. Rotation speed, 300 revolutions per minute. Linear drawing speed, 470 meters per minute. That's 28 kilometers per hour. The wire heats up from friction. Temperature exiting the die, 200 degrees Celsius. Cooled with water. After drawing, the wire is hard. Tensile strength, 1800 megapascals. Elongation, 2%. It's brittle. Heat treatment needed. Heat treatment. Heat treatment. The wire gets heated in a furnace to 1650 degrees Fahrenheit. Hold it there for 20 minutes. The steel structure reorganizes. Carbon dissolves into the lattice. Then it cools in air at a rate of 180 degrees per hour. Slow cooling. You get tempered steel. Hardness drops, but ductility increases. Elongation, 8%. The wire's now flexible. Ready for rope making. Strand twisting. Take 6 wires, diameter 0.08 inches. Twist them around a central 7th wire. Lay length, 4 3/4 inches. That's the distance one wire takes to complete one full wrap around the center. Helix angle, 15 degrees to the axis. Twist direction, right hand. Looking along the strand, the wires spiral clockwise. You get a strand, diameter 0.24 inches. Starting wire length, 3,300 feet. Finished strand length, 3,100 feet. The difference, that's what the twisting eats up. The strand bends easy. Bend radius, 6 inches. Strand strength, 70% of the combined wire strength. Losses from bending and friction. Rope stranding. 6 strands, 1/4 inch in diameter, twisted around a core. The core is organic. A hemp rope, 1/4 inch diameter. It's soaked in lubricant. Hemp is elastic. It absorbs shock loads. Stores lubricant inside the rope. There can be more strands. Standard construction is 6 by 7. 6 strands with 7 wires each. There are 18 by 7 ropes. 18 strands, 7 wires per strand. There's 36 by 7. More wires mean a more flexible rope. The diameter of a 6 by 7 rope with core 1/4 inch wires is about 3/4 of an inch. Breaking strength is 50 kilonewtons. That's 5 tons. Weight is about half a pound per foot. The rope gets wound onto a drum 6.5 feet across, 5 kilometers per drum. That's over 3 miles. Weight of the drum with rope is 8 tons. The ropes ship out to plants that make giant cables. Manufacturing giant ropes. United Offshore Services in the Netherlands makes ropes ranging from 4 3/4 inches to 21 inches in diameter. The factory houses a machine that's over 650 feet long. It twists finished ropes around a central core rope. Here's an example. They're making a rope that's 13 inches in diameter. They take 6 ropes, each about 4 inches thick, plus a central rope that's 4 3/4 inches. Then they twist them together. The rope spools get mounted on a rotating carousel. The carousel is nearly 40 feet across. It spins at 2 revolutions per minute. The ropes unwind from the spools. They pass through guide rollers. They twist around the central rope. The lay length is 71 inches. The lay angle is 20 degrees. Twisting speed is 11.5 feet per minute. In 1 hour, they produce 690 feet of rope. The finished 13-inch rope gets wound onto a spool that's 13 feet in diameter. Breaking strength? 9,700 tons. That means this rope won't snap until you load it with 9,700 tons. Marking and lubrication. The cable gets marked along its entire length with different colored paints. Red section, the start. Yellow, the middle. Blue, the end. Every 33 feet, a marker with a number. Then they lubricate it. They use lithium-based grease. Drop point temperature, 356 degrees Fahrenheit. The grease protects against corrosion and reduces friction between the wires. The cable runs through a bath of liquid grease heated to 176 degrees. The grease soaks into the core and between the strands. Then they apply an outer layer, anti-corrosion coating. It's a thick paste made from paraffin and corrosion inhibitors. Coating thickness, 0.02 inches. The final cable, length 558 feet, diameter 13 inches, weight 76 tons, breaking strength 10,700 tons. They move it with a crane rated for 165 tons. One end gets hooked. They lift. The cable hangs vertically. Lift height, 164 feet. You need a tower. At the factory, there's a tower 197 feet tall, specifically for this. Super long ropes. Hendrik Vader Group in the Netherlands makes the longest ropes in the world. Length, 920 feet. Diameter, 16 inches. Different technology. The machine travels along rails 1,000 feet long. At the start sit spools of rope. 8 spools. On each, a rope diameter 10 inches, length 920 feet, weight 110,000 pounds. Strength of each, 7,700,000 pounds. The machine starts moving. Speed, 6.5 feet per minute. The ropes unspool. They twist around a central rope diameter 10.25 inches. Lay length, 6.5 feet. The machine travels 1,000 feet in 2.5 hours. You get a rope diameter 16 inches, length 920 feet, weight 440,000 pounds. Strength, 31 million pounds. That's the weight of 80 tanks. At the end, they make a loop. They bend the rope back 15 feet. They splice the free end with the main rope. You get a loop 15 feet long. Loop diameter, 5 feet. The splice is locked with steel clamps. 10 clamps. Each clamp, 2 steel half-cylinders. Tightened with 8 M36 bolts. Torque, 590 foot-pounds. Transport and deployment. A rope 900 feet long, weighing 440,000 pounds, lies coiled on the factory floor like a snake. It needs to be loaded onto a ship. They use 3 forklifts, each rated for 55,000 pounds. They lift the rope at 3 points. Drive it to the dock. Distance 1,600 feet. Speed, half a mile per hour. Time, 30 minutes. At the dock stands a crane rated for 880,000 pounds. It grabs the rope by its loop, lifts it, lowers it into the ship's hold. The ship carries the rope to Norway, to the Åsgard oil and gas field in the North Sea. Sea depth, 980 feet. A floating production platform sits there. Platform weight, 110 million pounds. The platform is held by 8 anchors. One rope 16 inches in diameter runs to each anchor. Each anchor weighs 440,000 pounds. Sits on the seabed. The rope runs from the anchor to the platform. Rope tension, 2 million pounds in calm weather. In a storm, 6.5 million pounds. Safety factor, 5 times. The rope is rated for 20 years of service. Inspected every 3 months. They send down an underwater vehicle with a camera. Inspect every foot. Looking for broken wires, corrosion, wear. If wear exceeds 10%, they replace the rope.
Every year, the world mines thousands of tons of metals, but only one is so dangerous it can kill you even as dust, and yet helps us peer 13 billion years into the universe's past. That's beryllium, a metal lighter than aluminum but many times harder than steel. A metal without which the James Webb Space Telescope wouldn't exist. But there's one detail almost nobody talks about. Why does producing it feel like a chemical nightmare? And why does working with it become a deadly gamble? And what exactly are those factories hiding behind thick, protective glass? Subscribe so you don't miss out. You'll learn something that'll forever change how you think about metal. Let's jump straight to the numbers, because they're absolutely mind-blowing. Look at this block of metal. Appears to be just another gray hunk of iron, but try to lift it and you'll nearly clock yourself in the chin from the surprise. Beryllium has a density of just 1.85 grams per cubic centimeter. That's almost 30% less than aluminum, which we've always considered the gold standard for lightness. But here's the kicker. Despite being this lightweight, beryllium is 4 times stiffer than steel. Its elastic modulus hits an incredible 303 gigapascals. What that means is this material puts up insane resistance to any deformation. You could build a structure thin as paper, and it would still hold its shape under colossal stress. On top of that, beryllium has this exceptional ability to maintain its strength at high temperatures, making it absolutely irreplaceable in the aerospace industry. The extraction process, that's a whole chapter in the textbook of industrial survival. The primary source here is a mineral called bertrandite, mined in the deserts of Utah. The ore contains just 0.5% beryllium. To extract this metal, the rock gets crushed and dunked into sulfuric acid, turning everything into a chemical slurry. Then, through a series of complex manipulations with hydroxides and fluorides, they get pure beryllium fluoride. They mix it with magnesium in massive crucibles and heat it up to 2,400 degrees Fahrenheit. The magnesium grabs the fluorine, and shiny metallic grains settle to the bottom, so-called pellets, or beryllium pebbles. Each grain is only a few millimeters across, But it's from these tiny pieces that parts for spacecraft and military hardware will eventually be assembled. But this is just the beginning, because working with them directly is impossible. And here's where we get to the most dangerous part of the tour. Beryllium is a genuine toxic bomb. Its dust causes chronic beryllium disease, which basically makes your lungs shut down. All it takes is breathing in a microscopic amount of particles, and your immune system starts attacking your own tissues. The disease can show up years after exposure, when you've long forgotten that one day you spent at the facility. So nobody here pours the metal into molds like cast iron. Instead, they use powder metallurgy methods. Metal grains get ground into fine powder in special mills under vacuum. Every single dust particle has to be controlled. Then, they pour this powder into massive steel capsules and subject it to vacuum hot pressing. Imagine hundreds of atmospheres of pressure and temperatures over 1800 degrees Fahrenheit, simultaneously crushing this powder, forcing it to become a solid block. This goes on for hours until the structure becomes perfectly uniform. Why did the telescope engineers choose this hellish material for their mirrors? It's all about the cold of space. James Webb operates at Lagrange Point 2, about 930,000 miles from Earth, where temperatures plunge to minus 370 degrees Fahrenheit. Regular glass deforms unpredictably when it cools this much, expanding in one spot, contracting in another. But beryllium has a unique property. Its thermal expansion coefficient at low temperatures becomes virtually zero. It basically freezes in place. The shape stays constant no matter how brutal the cold gets. This made it possible to build mirrors that remain perfectly smooth even in the savage cold of deep space. Each of the 18 mirror segments measures 4.3 feet across but weighs just 44 pounds. If they were made from glass, each one would tip the scales at over 200 pounds, and the rocket simply couldn't lift off the ground. Each mirror was carved from a single block, removing 90% of the mass from the back to create a lightweight honeycomb structure. This is called lightweighting. The walls there are just a few millimeters thick. After that, polishing begins. It's done using computer systems that remove irregularities measured in nanometers. 1/1000th of a meter. That's the precision we're talking about here. If Webb's mirror were the size of the Atlantic Ocean, the biggest bump on its surface wouldn't be taller than a regular coin. Then the mirrors are taken to a cryogenic chamber, where they're cooled to space temperatures, microscopic warping is measured, and then they're polished again to compensate for those changes. This cycle was repeated dozens of times over several years. Now take a look at this color. We're used to seeing telescope mirrors in gold, but underneath that gold lies pure beryllium. The gold is only applied at the very end through vacuum deposition. The gold layer is just 100 nanometers thick. That's 1,000 times thinner than a human hair. The entire massive mirror, covering about 270 square feet, used only about 1.7 ounces of gold. That's like 3 or 4 wedding rings rolled out across a giant surface. Gold is essential because the telescope searches for infrared radiation from the very first stars that ignited 13.5 billion years ago. Beryllium provides rigidity and stability, while gold delivers perfect reflection in the precise wavelength range needed. At this facility, safety protocols look like paranoia. But it's justified paranoia. See those yellow lines on the floor? You can't cross them without special footwear. The air in the shop completely refreshes every 3 minutes. Beryllium levels in the air must not exceed 0.2 of a microgram per cubic meter. That's so small you couldn't even see it under a microscope. But sensors are everywhere. After every shift, each worker goes through a special shower, and their clothing gets disposed of as hazardous waste. That's the price we pay for the ability to peer into the depths of space. But beryllium isn't just about space. Look at these tiny components for aircraft engines. Because beryllium conducts heat better than most metals, it's perfect for parts that need to cool down fast. Its thermal conductivity is around 210 watts per meter Kelvin. It pulls heat away faster than aluminum and doesn't melt until 1287 degrees. This lets planes fly faster and engines run more efficiently. Here's another wild fact you probably won't hear in chemistry class. Beryllium is almost transparent to X-rays. Take an X-ray through a steel plate, you'll see nothing. But with beryllium, the rays pass through like it's not even there. That's exactly why the windows in every X-ray machine and CT scanner at hospitals are made from beryllium foil. It lets doctors get crystal clear images of your body without losing radiation power at the machine itself. So what does all this cost? If you want to buy a kilogram of pure beryllium, expect to shell out anywhere from $800 to $1,000. But that's just raw material. The cost of a finished part can be 10 times higher or more because of how difficult it is to machine and all the safety precautions required. A single web mirror segment costs millions of dollars when you factor in all the years of testing and polishing. And even with these insane prices, global beryllium production doesn't exceed a few hundred tons per year. That's how rare and difficult it is to work with. Thanks for watching. Hit that like button if you love real science as much as I do. See you at the next classified facility.
Imagine a gas capable of changing the course of history. It can disinfect water, create plastic without which modern life is unthinkable, and at the same time become a deadly weapon. This is chlorine. Annually in the United States, over 12 million tons are produced, as much as 120 Gerald Ford aircraft carriers weigh. But the real mystery isn't in the numbers. It's hidden in the technology itself. How does simple salt water, with the help of electricity, give birth to 3 products that support entire industries? Watch carefully. At the end of this video, you'll learn a fact that will forever change your understanding of this invisible foundation of modern civilization. The United States is one of the world's largest producers of chlorine. Annually, factories in the country produce over 12 million tons of this gas. This figure simply doesn't fit in one's head. Imagine the weight of the Gerald Ford aircraft carrier, the world's heaviest military vessel. That's about 100,000 tons. This means that in 1 year, American industry produces as much chlorine as 120 such carriers weigh. Everything begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. It's either mined in mines or, much more efficiently, pumped from underground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated saline solution called brine. And it's precisely this concentrated salty solution that's our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals. Therefore, before the main show begins, the brine undergoes thorough purification. It's passed through an entire series of tanks where, with the help of chemicals, all impurities are precipitated and filtered from it. At the output, we obtain a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. These are electrolyzers or cells. It's precisely here that all the magic will occur, or more accurately, all the chemistry. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure saline solution is poured. And into this solution are immersed two electrodes, a positively charged anode and a negatively charged cathode. Now to these electrodes is applied a direct electrical current of colossal force. And here the breakdown begins. The salt molecule in water breaks down into positively charged sodium ions and negatively charged chlorine ions, and the electrical field forces them to move. The positive sodium ions, like a magnet, are attracted to the negative cathode, and the negative chlorine ions to the positive anode. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together and on the anode surface begin to appear tiny bubbles of greenish-yellow gas. This is our chlorine. The main resource for chlorine production is electrical energy. The chlor-alkali industry is one of the largest consumers of electrical energy in the United States. To produce 1 ton of chlorine requires approximately 2,500 kilowatt-hours of electricity. Now let's multiply this by 12 million tons per year. It turns out that this industry annually consumes about 30 billion kilowatt-hours. That's more than the annual electricity consumption of entire states such as Vermont or Wyoming. But they don't transform into metallic sodium. Instead, electrical current splits the water molecules present in the solution into hydrogen and hydroxide ions. At the cathode are released bubbles of pure hydrogen. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming sodium hydroxide, or caustic soda. This is our second incredibly valuable byproduct. But here arises an enormous problem. We've just obtained 3 substances, chlorine, hydrogen, and caustic soda, and they must not be mixed under any circumstances. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react, forming bleach, which we don't need at all. This membrane, made from special polymer, resembles a bouncer at a nightclub. It allows positive sodium ions through, permitting them to pass to the cathode, but blocks negative chlorine ions, preventing them from entering the cathode space. Thus, chlorine is born and collects in one part of the cell, whilst hydrogen and caustic soda collect in another. Now we need to gather our harvest. From the anode chamber is continuously pumped wet, hot, greenish-yellow gas. First it must be cooled, then it must be dried. Chlorine is incredibly aggressive, especially in a wet state. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. It's compressed under enormous pressure and simultaneously cooled. Under this double assault, the gas transforms into a transparent, amber-yellow liquid resembling oil. This liquid chlorine is far more convenient to transport and store. It's poured into special thick-walled steel tanks or railway wagons. Every step of this process occurs under conditions of absolute seal, because leakage of this gas is deadly dangerous. And what about our byproducts? they're no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the factory itself or sold. And the caustic soda solution that formed is pumped out, concentrated, and sold. And so, from simple salt water, passing through it an enormous quantity of electricity, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products. Now let's look at where all this enormous quantity of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's merely a drop in the ocean. In reality, less than 5% of all chlorine is used for water disinfection. And where does the remaining 95% go? It's a key building block for other products. About 40% of all chlorine goes to producing this universal plastic. Vinyl windows in your house, water pipes, medical drips, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% approximately is used for creating thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. And chlorine is also a key component for bleaching paper, giving it that very clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we obtain approximately 1,100 kilograms of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business.
Today we're going on an incredible journey. From massive crankshafts that power ocean vessels to precision railroad components that keep millions of passengers safe. Settle in and let's dive into the mesmerizing world of industrial manufacturing. Here we're witnessing something truly impressive, the machining of a massive marine crankshaft weighing over 15 tons. This isn't your typical workshop project. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into rotational motion that propels these ocean giants across our seas. The star of the show, a revolutionary vertical boring mill. Rising nearly 3 stories tall, this engineering marvel features a 20-foot diameter faceplate capable of machining parts up to 65 feet long. The machine's spindle delivers an impressive 1,600 horsepower while maintaining accuracy tolerances of just 4/10,000ths of an inch. That's thinner than a human hair. An advanced computer numerical control system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. Watch as the massive crankshaft rotates at a carefully controlled speed of 15 revolutions per minute. Carbide cutting tools, each costing more than a luxury car, slice through hardened steel like butter. The cooling system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny deviations can spell disaster. The real magic happens during the finishing passes. Using diamond-tipped tools, surface finish reaches an incredible 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains intact. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to where they've redefined what heavy-duty really means. This isn't just another CNC lathe. This is a mechanical monster engineered to tackle the roughest, toughest machining jobs in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast can handle parts up to 5 feet in diameter and 40 feet long, weighing up to 25 tons. The main spindle generates 400 horsepower through a precision planetary gearbox, delivering massive torque at low speeds. Watch the machine attack this massive steel workpiece with aggressive roughing cuts. The cutting parameters are mind-blowing. Depth of cut just over ½ an inch, feed rate around a 32nd of an inch per revolution, removing over 200 cubic inches of material per minute. High-pressure coolant jets at 1,000 pounds per square inch blast away continuous ribbons of steel chips that could fill a pickup bed in just minutes. Advanced vibration damping and thermal compensation systems maintain dimensional accuracy within 0.02 of an inch across the entire part length. The CNC system with adaptive control technology automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist intuition built right into the machine's brain. Step into the world of railroad wheel manufacturing, where safety and precision aren't just priorities, they're matters of life and death. Every single day, millions of passengers trust their lives to these wheels, which must withstand enormous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains racing across the European countryside to heavy freight locomotives hauling cargo across the American plains, the wheels we're about to see represent the culmination of over 150 years of railroad engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 2,190 degrees Fahrenheit in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support railcars weighing 25 tons. The wheels are then normalized in computer-controlled furnaces, cooling slowly over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now the precision work begins. Each wheel blank is mounted on state-of-the-art CNC wheel lathes, masterpieces of German engineering capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive chucks 10 feet in diameter that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a three-dimensional map that guides the machining process. This is where artistry meets engineering. The wheel profile isn't just a simple curve, it's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the lathe creates the tread surface with its precise 1-in-20 taper, the flange that keeps the train on the rails, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser sensors measuring to within 0.01 millimeters. Surface finish must be perfect. Any imperfections will create wear that could lead to derailment at 200 miles per hour. Here we're looking at one of the most demanding machining operations out there, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision holes through materials that could stop a tank round. These operations are common in heavy industrial applications like hydraulic cylinders for mining equipment, deep hole drilling for oil drilling, and cylinder blocks for massive diesel engines. The horizontal boring mill dominates this operation with its massive spindle assembly, capable of reaching several feet into the workpiece. The boring bar itself, a precision tool weighing hundreds of pounds, must remain absolutely rigid while cutting forces try to deflect it. Advanced vibration damping systems and precision spindle bearings ensure cutting tool stability. The cutting insert, $300 of carbide engineering, must maintain a sharp edge while removing cubic inches of steel per minute. Watch as a massive cutting tool begins its journey through steel, creating this perfect 8-inch hole. The cutting parameters are carefully calculated. Too aggressive, and the boring bar will deflect. Too conservative, and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling, but to flush away the continuous stream of steel chips that could jam the operation. The machine's computer numerical control system automatically compensates for boring bar deflection, ensuring the final hole diameter stays within a tolerance of 0.01 inches across its entire length. Now comes facing, creating a perfectly flat surface perpendicular to the hole. The facing head, equipped with multiple cutting inserts, machines the surface at feed rates measured in thousandths of an inch. Once complete, this component could become part of a mining excavator's hydraulic cylinder, where it'll control movements of machinery weighing hundreds of tons. The precision we just witnessed ensures these systems run reliably for decades, moving mountains one bucket at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, sophisticated geometries, and precision threads in a single setup. These parts might look simple, but they represent the pinnacle of machining mastery, demanding perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turned diameters, each with different tolerances and surface finish requirements. Notice the stepped geometry requiring different cutting tools for each operation, the internal threading that must align perfectly with external features, and the complex radii that seamlessly blend surfaces. The threading operation demands specialized thread cutting tools and precise spindle synchronization. The computer numerical control system coordinates spindle speed with carriage speed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Single-point threading tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, correct thread form angles, and perfect surface finish all combine to create threads exceeding commercial standards. The completed part undergoes comprehensive quality inspection using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish gets verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instruments, where failure isn't an option.
Take up a stone. Bright red, heavy, looking like dried blood. It doesn't smell, doesn't burn, doesn't radiate. Just a beautiful mineral. Now throw it into a furnace at 1300 degrees Fahrenheit, and liquid metal flows out. Silvery, heavy, cold to the touch. The only metal on Earth that stays liquid at room temperature. Mercury. A substance that has mesmerized alchemists for millennia, poisoned kings, and powered industry. And it's extracted from a stone that looks like a gemstone, but is actually just ordinary sulfide. Today, we're at a mine and processing plant where red rock turns into liquid silver. If you're into deep dives like this, subscribe and hit the bell so you don't miss new episodes. This red rock is called cinnabar, mercury sulfide, one of the few natural compounds where mercury shows up in Earth's crust. The chemical formula is simple: one mercury atom, one sulfur atom. Basically, nature locked liquid metal inside a sulfur cage, and to get it out, you've got to break that cage with heat. If you crack a chunk of cinnabar, the fracture surface reveals crystals with a diamond-like shine. The beauty's deceptive because the powder from this mineral is poisonous. Cinnabar was known even in ancient times. Egyptians used it as pigment, Romans painted palace walls with it, and Chinese alchemists believed the red ore was the key to immortality. Deposits are scattered across the planet, but the main ones are in Spain, Slovenia, China, and Kyrgyzstan. The Spanish mine at Almaden operated for nearly 2,000 years and gave the world more than a third of all mercury ever extracted. The ore sits in volcanic activity zones because mercury rises with hot solutions from deep within Earth's crust and settles in rock fractures as bright red veins. Sometimes cinnabar is so rich that the rock looks like someone painted it with scarlet dye. Mining starts underground. Miners drill into the rock with pneumatic jackhammers, place charges, and blast, bringing the whole face down. They load the ore into mine cars and haul it to the surface. It's hard, dangerous work. Even down in the mine, mercury vapor seeps from the rock, so ventilation runs at full blast. Mercury content in the ore is usually low, 1 to 12%. The rest is waste rock, sandstone, clay, quartz. But even 1% is worth going after because mercury fetches a high price. At the surface, the ore gets crushed in jaw crushers. 2 steel jaws squeeze the rock, breaking it down to gravel size. Then, vibrating screens sort the pieces by size. The fines go straight to the furnace. Oversized chunks loop back for another round of crushing. Dust is a whole other problem. It carries mercury, and breathing it is dangerous. So the crushing plant runs heavy exhaust and wet dust suppression. Workers wear respirators, and at the entrance, there's a mercury vapor monitor. If the needle swings into the red, they shut down the plant and air it out. Now comes the most critical step: roasting. The principle is simple yet brilliant. Heat cinnabar to 1100 to 1300 degrees Fahrenheit in air, and the sulfur bonds with oxygen and escapes as sulfur dioxide gas, while the mercury vaporizes. 2 substances locked in stone for millions of years part ways forever. One into the air, the other into a pipe. Roasting furnaces come in different designs, but the classic is a rotary kiln. Picture a massive steel drum, 60 to 100 feet long, set at a slight angle. Ore gets fed in from the upper end, burners fire from the lower. The heat inside is so intense, the furnace walls glow a dull cherry red. The kiln rotates slowly, tumbling the ore, gradually pushing it downward as it heats up more and more. When the temperature hits the sweet spot, the cinnabar breaks down. Sulfur burns with a bluish flame, and mercury vapor, invisible and deadly, rises and travels with the flue gases into the condensation system. The spent rock, now stripped of mercury, spills out the lower end of the furnace into a waste pile, gray, lifeless, having surrendered everything valuable to the fire. Condensation is the moment when invisible vapor transforms into that actual liquid metal. Gases from the furnace pass through a long system of pipes and chambers that gradually cool down, usually with water fed through jackets on the outside. Mercury condenses first. Its boiling point is only 675 degrees Fahrenheit, so when the gases cool below that mark, silvery droplets start settling on the condenser walls. They trickle downward and collect in receivers, steel or ceramic containers. The sight is mesmerizing. From the pipe, as if from nowhere, heavy silvery liquid drips down, falling into the collector with a distinctive, soft sound. Not a clang, not a thud, but something in between. Because mercury is viscous and heavy, 13.5 times heavier than water. A quart of mercury weighs more than 28 pounds. Try picturing a quart of milk that weighs as much as a bucket of cement. The raw mercury from the condenser isn't ready for sale yet. It's swimming with impurities, soot particles, water droplets, traces of other metals. It's cleaned in several stages. First, they filter it through chamois leather or special fabric. Mercury passes through the pores while the dirt stays behind. Then, they wash it with diluted nitric acid, which dissolves impurities like zinc, lead, and tin, leaving the mercury itself untouched. The final purification is vacuum distillation. Mercury gets heated in a vacuum, where it evaporates at a lower temperature, while impurities with higher boiling points remain at the bottom. They collect the condensate, and now you've got mercury at 99.9% purity. It's poured into standard steel flasks holding 76 pounds. That's the international standard called a flask. The container's small, about the size of a thermos, but lifting it one-handed? Not easy. All because of that incredible density. Safety at a mercury plant is a world unto itself. Mercury vapor has no color and no smell, but it's extremely toxic. Just a few hours of breathing it can give you serious poisoning. Chronic exposure destroys the nervous system. That's why hatters in the 19th century went mad. They used mercury to treat felt and inhaled the fumes for years, hence the phrase, mad as a hatter. In a modern plant, the entire facility operates under negative pressure. Air is constantly pulled inward, not pushed outward, so vapors don't escape into the atmosphere. Floors are coated with a special non-porous covering. If mercury spills, the droplets won't roll into cracks, but stay on the surface where they can be collected with a specialized vacuum or a sulfur trap. Sulfur powder binds mercury into harmless sulfide. Every worker carries a personal dosimeter that measures accumulated vapor exposure per shift. Exceed the limit, and you're pulled off the floor until your levels normalize. Where does all this mercury go? Historically, the biggest consumer was gold mining. Mercury dissolves gold, forming an amalgam. You then heat it up, and the gold evaporates out. Conquistadors in South America use this method, and it's exactly why the Spanish crown exploited almaden for centuries. Today, amalgamation is officially banned in most countries because of the catastrophic environmental damage. But in artisanal mining across Africa and Southeast Asia, millions of prospectors still use it. Poisoning rivers, poisoning soil. Other applications? Chlor-alkali industry, thermometers, barometers, mercury lamps, electrical switches, catalysts. But the world is slowly moving away from mercury. In 2013, the Minamata Convention was signed, named after a Japanese city where, in the 1950s, thousands of people suffered devastating poisoning. Mercury leaked into the bay from a chemical plant. It built up in fish. And the people who ate that fish started losing their sight, their hearing, their coordination. The Minamata tragedy became a symbol of mercury pollution for decades to come. Mercury production worldwide is plummeting. Back in the mid-20th century, mines pulled out up to 10,000 tons a year. Now, less than 2,000. Most mines have shut down. The famous Almadine in Spain stopped operations and turned into a museum. These days, mercury increasingly comes from recycling, old thermometers, lamps, industrial waste. But humanity can't completely abandon it yet. Some chemical and electrochemical processes simply have no substitute. When you stand next to a flask where this heavy, silvery liquid sloshes around, it's hard to believe that an hour ago it was part of a red rock that sat underground for millions of years. Cinnabar guarded mercury like a safe guards valuables, and only fire could pick that lock. An ancient process, simple at its core, dangerous in execution, and still without an alternative. Every year, the world produces over 5 million tons of structural steel. and almost all of it is born from rusty scrap. Old cars, dismantled ships, demolished bridges get melted down and transformed into I-beams, the steel backbone of modern cities. From the outside, it looks simple, a piece of metal with that distinctive I-shaped profile. But this shape is the result of engineering genius, allowing a single beam to support loads of several hundred tons. A skyscraper being built somewhere in the world right now might contain a piece of armor plating from a warship, melted down and born again. This isn't just metal, it's history, sealed in steel. How does a mountain of rust become a precision structure with tolerances measured in fractions of a millimeter? And why is every modern building taller than a few stories impossible without this unassuming component? Stick around till the end. There's a moment we'll show you that's almost never seen publicly. The genius of the I-beam is in its shape. When it bends, the main load hits the top and bottom edges of the cross-section. That's where most of the steel lives, in those horizontal flanges. The thin vertical web in the middle, it just holds the flanges apart at the right distance. This gives you maximum strength with minimum weight. And that's exactly why this profile shows up everywhere you need to span a gap without wasting material. If you rolled that same volume of steel into a flat rectangle, it'd hold a fraction of the load. That I-shape isn't about aesthetics, it's math. One properly installed heavy I-beam can handle hundreds of tons. Picture a column of fully loaded semi-trucks standing on a single piece of steel. That's the real power of shape. But this story doesn't start in some gleaming factory. It starts at a massive, noisy yard that looks like a graveyard for metal dinosaurs. This is a scrap metal depot. Mountains of old cars, sliced up railroad cars, construction wreckage, and industrial junk, all waiting to be reborn. If stories about the hidden life of metal grab you like this, subscribe to the channel right now and hit that bell so every new episode lands straight in your feed. A giant crane with a powerful electromagnet descends onto this pile, and with a metallic screech, tons of old iron stick to it. This scrap is the main ingredient of the entire production process. It's loaded into a massive steel basket and sent to the melting shop, where a fiery baptism awaits. Steel is the absolute champion of recycling. The recycling rate for structural steel reaches 98%. That means practically all the metal from demolished buildings, old bridges, and scrapped ships returns to production. On average, a new I-beam is 90% recycled metal. A skyscraper being built today might contain a piece of a car from the 70s, a railroad rail from the 30s, and armor from a World War II ship. This isn't just a piece of steel, it's compressed history, remelted for new service. This is the special magic of manufacturing that almost never gets talked about. The steel cycle is virtually infinite, and each generation of cities passes its metal to the next. Every year, the US alone produces over 5 million tons of structural steel, and most of it, I-beams. That scale is hard to wrap your head around, so let's try. The steel in the Golden Gate Bridge weighs about 83,000 tons, which means American mills produce enough beams in 1 year to build more than 60 of those bridges. 60 Golden Gate bridges, every year. And that's just one country. The heart of the mill is the electric arc furnace, a giant bucket the size of a small house where scrap metal gets dumped with a deafening roar. The sight alone is incredible, tons of twisted iron crashing inside, filling the bucket to the brim. From above, 3 massive graphite electrodes descend into the furnace, each one as thick as an old-growth tree. The operator flips the switch. An electric arc flashes between the electrode tips and the metal, an artificial lightning bolt striking with colossal force. The floor fills with a deep, ear-splitting roar, and the light from the arc is so bright it blinds you even through protective glass. The temperature inside instantly rockets to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts melting, transforming into a boiling, blinding lake. Special additives get thrown into this molten bath: manganese, silicon, sometimes chromium or nickel, to create the exact grade of steel needed. Strong yet flexible, able to withstand massive loads without shattering like glass. The entire melting process takes 40 to 60 minutes, and in that time, tons of rusty junk completely transform into uniform liquid metal. Once the steel's ready, it needs to go from liquid river to something solid. The molten metal gets poured into a continuous casting machine. Glowing liquid flows into a special water-cooled copper mold. Passing through it, the outer layer of steel solidifies, forming a thin shell. From there, this still semi-liquid billet continuously gets pulled downward, passing through a water spray zone where hundreds of nozzles shower it with water, forcing it to solidify completely. Out of the machine crawls an endless, red-hot, massive steel billet, square or rectangular in cross-section. This is called a bloom. Automatic cutters hiss as they slice off pieces to the right length, 20, 25, 30 feet. This is our blank, the chunk of dough we're going to shape into a beam. Looks like an ordinary rectangular bar. No hint of the form it'll take in just a few minutes. These hot but now solid blooms head to the next furnace, the reheating furnace. Think of it as a giant tunnel with flames roaring inside. The blank creeps slowly through, and its temperature climbs back to the perfect working state, around 2200 degrees Fahrenheit. It becomes plastic and soft, like clay, ready for the most critical step, rolling. The quality of this heating determines just how precise and uniform the final profile will be. And now, the real spectacle begins. The bloom, heated to a blinding orange glow, rolls out of the furnace and enters the rolling mill. This is a series of gigantic steel rollers, like enormous rolling pins positioned one after another. But these rollers aren't flat. They have special grooves or calibers whose shape gradually approaches that of an I-beam. The bloom crashes into the first pair of rollers. They squeeze it with incredible force, thousands of tons, making it slightly thinner and longer. At the exit, the next rollers catch it, compressing it at a different angle and starting to form the flanges and web of the future beam. Step by step, passing through dozens of these roller pairs, the shapeless bar visibly stretches and takes on the familiar I-beam profile. A glowing chunk 20 feet long extends into a fiery ribbon stretching several hundred feet. The entire shop fills with thundering noise, the screech of metal, and the hiss of water cooling the rollers. This is one of the most powerful industrial spectacles you can witness with your own eyes. When the beam emerges from the final finishing roll, it already has perfect shape and dimensions, accurate to within 1/10 of a millimeter. Hot, long, like a fiery serpent, it travels along a roller conveyor to a massive cooling table. This giant grid is where the beam slowly cools down, releasing its heat to the air. This process can't be rushed. Cooling too quickly creates internal stresses in the metal that can later lead to deformation or microcracks, invisible from the outside. During cooling, the metal shrinks slightly, and sometimes the beam can warp just a bit. This is normal and predictable. Engineers account for this in the manufacturing process. To correct any deviation, the cooled beam is sent to a straightening machine. It runs the beam through a system of rollers that press with calculated force and squeeze out any deviation from straightness. What comes out is a perfectly straight steel profile, ready for final operations. Now we've got a perfectly straight beam, but it's not ready to ship just yet. Time for the finishing touches. First, they cut it to the exact lengths the customer ordered. Giant circular saw blades about 6.5 feet across do the job. With a deafening roar